Yeah, why is this?
So get the chair out of the way. Chair's out of the way. I guess people don't like me today.
Okay.
We're all set.
Mhm.
Cursor there. Okay, so here we are. You and me, and all of you out there. So what we'll be doing for the first half of today is we'll be going over the midterm. Your performance on the midterm is probably going to be just as awful as the pretest.
Thank you.
So you should expect to score in the mid-70s on this exam.
Mhm.
You won't really start to see the improvement until you get to the tri-term, which will be 2 weeks from now. 3 weeks from now. 3 weeks from now. What do you think of the exam? Easy? Hard? About the same?
I thought it was hard because a lot of stuff that I have not seen yet, I was searching through the book. So
Okay. About 60% of what was on the exam we've covered. So there's still about 40% that is completely new and foreign. So yes, you're seeing material on the midterm that you haven't seen before, because what it is it's half of a released exam. So you got the first 50 questions during the pre-test. Now you got the second 50 questions during the second part of the exam. So yeah, you should be able to be comfortable with it. But hopefully you are more comfortable with the book and where to find things in the book and how to use your reference materials. Because again, that's going to be a really important when you take the real exam, is to how do you shepherd your resources and being able to find the answers in the book, because on a certain level, this exam is a find a word. It's finding the information somewhere hidden in the book.
Right.
So the only way for you really to get better at that is to, well, do it. And hopefully you're getting that practice through going through the practice tests, going through the midterm. So without any further ado, shall we start with question 1? The primary reason that most companies implement Six Sigma is to, what do we think?
I said to improve profit.
Yes, it's all about the money. Remember that story that I told about how I was presenting at a conference in Slovenia, and the guy talked about the differences in Six Sigma all around the world, and I, being one of a couple Americans at the conference, ended my slides with the entire business case for why my project made sense, whereas this guy had just said that Americans, it's all about the money. Well, we're in the States, so Six Sigma is all about the money here. So the answer there is C, improve profit.
Okay.
So now going on to question 2. The term used to describe the risk of a type 1 error in a hypothesis test is, this is actually a straight definition question. And if you look in the book, you can find it. And the answer here is, what do you think?
I could not find the definition. Type 1 error, I read that it's something when it is rejected when it actually can be accepted. Type 2 is when you accept something which is unacceptable. But going down to the other convert, I was trying to see that.
Okay.
Is it beta risk or alpha, beta?
Well, type 1 error corresponds to alpha.
Alpha, yeah. So
And type 2 corresponds to
beta.
beta. There you go. Kind of, some things are that straightforward.
Yeah, but this one is type 1.
So type 1 is alpha, and alpha is your level of significance.
Okay.
And your level of significance is directly related to your confidence level. 1 minus your confidence level gives you your level of significance.
Okay.
Or 1 minus your level of significance gives you your confidence level. So on our hypothesis test, when we get to that next week, we'll be working with alpha being 5%. With the general rule of thumb being alpha being 0.05 is sort of the standard rule of thumb that you use unless you're in a special circumstance. So alpha is generally 0.05, which corresponds to a 95% confidence level, because 1 minus alpha equals your confidence level.
So alpha is 0.05, you said?
Generally, yes.
And 1 minus alpha.
Will give you your confidence level, which is generally 95% if you're at alpha being 0.05.
Okay.
And I apologize for jumping between decimals and percentages there. We're just going over the exam.
Cool. So I don't miss anything.
You missed question 1.
Okay, cool.
You missed question 1, which the answer is improved profit. Because Six Sigma is all about the money. Then we were just answering question 2.
Yeah,
So question 2 is about type 1 error. So type 1 error corresponds to alpha.
See.
And alpha is your level of significance. And the relationship between your level of significance and your confidence level is 1 minus your level of significance is your confidence level. Or 1 minus your confidence level is your level of significance.
So I didn't know, I couldn't find it, but I found the error 1 is alpha.
Yep.
Alpha, but so what?
So that you just said, so which one would it be, confidence or level?
Level of significance. Type 1 error is alpha. Type 1 error and alpha are synonymous. And alpha is defined as your level of significance.
Okay.
Yeah.
Yep, mark it up in your book.
Alpha, okay. Can you repeat this
Yep.
one more time?
Type 1 error is your alpha risk. And alpha corresponds to your level of significance. So when we get to our hypothesis testing section next week, we will be working at a 5% level of significance. So alpha will be set to 0.05.
In the book, it wasn't that.
It was nothing.
Nothing. I went to the 280 page and I was.
Yeah. Me too.
Maybe I
You
should
mean there's
read
actually a value add to me talking about this stuff? You can't just read the book?
No.
Oh, there's a reason to come here.
The question is, there is another 2 questions that are so
Yeah, they're-
similar, but then
Yep.
I have no idea what it
That's why we're here, and that's why we go through every question.
is. Cool.
So let's go through the distractors, because there's some definitions in there that you should be familiar with.
Mhm.
Power. Power is defined as 1 minus beta. And we will get to power when we talk about our hypothesis test and how that relates to your sample size. Your confidence level. Your confidence level is how confident you are in a given result. It's defined as 1 minus alpha. So if alpha is 5%, your confidence level is 95%. If you're at a 99% confidence level, alpha is 1%.
Okay, so now you're explaining to us why
No,
other.
I'm going through each one of the distractors and defining what those terms are, because it's important that when you're reviewing these exams on your own to recognize that though you're only getting 50 questions, you're really getting 200 questions, because each one of the distractors, each one of the wrong possible answers could be a question unto itself. So they very easily could have asked you a question that is the term used to describe 1 minus the type 1 error in a hypothesis test is, and there it would have been a question on confidence level. I think there actually is a question on power later in the exam.
Mhm.
So could be question 1 minus type error and the rest counts will be confidence level?
Correct.
Then?
Correct. Wow, you killed a lot of trees.
This is for good cause. She was, can get certificate.
Okay, then we have level of significance, which we defined as alpha, which is for most of hypothesis tests, 0.05. And then we have beta risk, which is the risk of a type 2 error. And when we do our hypothesis test section, we will spend a lot of time making it clear to you the difference between a type 1 error and a type 2 error, and we'll make an analogy to the criminal justice system that I think will explain it to you. As a coming attraction, the O.J. Simpson case is beta.
There was nothing in the book.
Yep, it's hidden in the book. It's in there. It's just not in a very clear way.
Yeah.
So the first one was?
But the first one was profit.
1C and 2C. Yes?
Yes.
Cool.
Yeah. 3. One characteristic of attribute data is that it is always. Yes!
I found it!
And it was
It
a
was in the parentheses.
and it was a question that we talked about a lot when we went over the pretest. The easy way to remember the difference between discrete data and continuous data is in discrete data, if you put a decimal point, it doesn't make sense.
So,
3B.
B, yes.
number 2 was?
2C.
2C.
1C, 2C, 3B.
Okay, so 4. Which of the following tests may be used to determine whether a sample comes from a population with an exponential distribution? So this is a question about hypothesis tests, and we will get to our hypothesis testing section next week.
Exactly. That's why.
We haven't gotten there yet, but as a coming attraction, the t-test. That's what happens when you sit down with doilies and drink out of very dainty chinaware and you see if oolong tastes the same as black, as green.
So this
The
is
t-test.
No, no. Yes,
T-test. Not getting it.
No. T-test, I know what it is.
The tea, the.
Yeah, I'm talking about drinking
England,
tea.
Okay.
For different types of tea. You sit down with little doilies and a little tea
Yeah.
set and a little dainty chinaware.
With
And
scones and
Yeah,
everything.
there you go.
But this is.
This is a hypothesis test. The t-test is a hypothesis test for means. So if you're comparing one sample to a known standard or two separate samples to each other, we would perhaps use the t-test. And when we get to our hypothesis test section, you'll have a decision tree that makes it quite clear as to which hypothesis test to use in which situation. So that's the t-test. Then we have the f-test. The f-test is what happens when you fail the test. But more importantly, it is a hypothesis test for variance or standard deviation. So it allows you to answer the question of, is the variance from my first sample the same as the variance to my second sample? You most often use the f-test after you do a continuous improvement activity, because one of the goals of Six Sigma is to decrease your variation. So you use the f-test to say, hey, was my project successful? Did I actually decrease the variation? So you would do an f-test comparing the before to the after. And hopefully the hypothesis test indicates that there actually was statistically significant improvement. If not, you wasted everyone's time. So the f-test is a hypothesis test used for variance or standard deviation. Remembering that the variance and the standard deviation have a well-defined mathematical relationship between the two. Remember what it is?
Mhm.
What's the relationship between variance and standard deviation?
Square root. Variance is equal to square root of standard
Standard
deviation.
So the variance is equal to the square root of the standard deviation. Is that right?
Yeah. Variance is equal to sigma.
Variance
Sigma
is
square of standard deviation.
sigma squared,
Square
and standard
is sigma.
is sigma.
Sigma. Okay, so I said opposite.
Yeah, you said it backwards.
Backward.
Yep, that's
I
why.
knew the right thing in my mind though.
Yep, writing it down. That's why writing it down is
yeah,
always
so
helps.
a square root of variance is sigma.
Yeah. So make sure you just keep those straight in your head. However, it works in your head. Variance equals sigma squared, and standard deviation equals just sigma. Yeah, STD. Which is sort of a bad thing to get, but it's okay in this case. Come on, you get here late and you don't think my jokes are funny?
I didn't hear
No,
this
I'm
one.
focusing on the right.
Oh.
No, you're failing the test.
Okay.
I was saying an STD is a bad thing to get, but it's okay in the board.
Now
okay?
we got it.
Yeah,
It's
yeah,
on the
okay.
board.
There we go.
The first one is C.
What?
First one is C.
Yeah, profit. It's all about the money.
That's the only one
You
I got
remember
right,
we
and the
discussed
discrete
when
I
he
got
said-
right.
Sweden was
Yep.
something and in different country.
Yep.
And
I
America
thought
was
process
profit and
improvement,
he
but-
was the next one. She was not there.
Yeah, I was
It's
here,
all about the
but in
money.
Okay,
book,
can you
It's
tell
all
us
about the
say
money.
that.
Money. It's all about the money.
Tell her one more time. That was
Oh, I already
very
told the
good
story.
example. This
So-
is very good example.
Yeah, so I spoke at a conference in Slovenia, and there was a guy in front of me, directly in front of me, that was from Sweden, and he was talking about the way Six Sigma is implemented all around the world. And this guy was an engineer at Siemens. So he first talked about how implementing Six Sigma in Germany, it was all about the metrics and hitting your numbers, and your success or failure of your project was all about the numbers. And in Sweden, it was more about, did the team feel like they were working together, and how did the team feel about the project? That's how success was defined. And in Japan, well, Six Sigma didn't quite work over there because there was some sort of cultural resentment. And then he finished up by talking about Six Sigma in the States and said, in the States, it is all about the money. Nothing else matters. Did your project make money or did it lose money? If you made money, thumbs up. If you lost money, you're dead.
That's how I memorize.
And then since this was a mostly European crowd, they all kind of a good laugh at the Americans being all about money. And here I was, one of 2 or 3 Americans in the conference, and then I go up there and the last 5 slides are all about money. It's like, just to conform to type, now the American is going to talk about money. Yeah. So that Six Sigma in the States is all about the money. It makes the
And
world.
you thought this
But the
about
book says
improved
for
product.
improvement.
But why is
thought,
the
see,
reason
I
of
put
this
an
thing?
arrow there, but I circled here.
I
because
immediately said
eventually
to
it comes.
improve
I
product. Why you
experienced
want
that
to
in my own
improve
company.
something? To get more money from it.
Yeah.
You know, even to get a project
the point?
clear, if you say that this in the end will improve something in efficiency or bring the money, that's when you really get a project chart.
It makes the world go round. That
You
clinking,
see,
clanking
it is very
sound of money, money,
strange.
money,
I
money,
notice
money,
when
money.
you talk about efficiency improvement, people are getting so resistant and scared they will lose their jobs.
Yeah,
So it is about money because they are afraid they will lose it because company will gain and they will terminate some position. That's how I.
yeah. When we talk about lean, I'll show you an acronym that people think lean stands for. Less employees are needed.
Yeah.
Lean everywhere. Take the waste.
Yeah,
out.
lean, but making it an acrostic. Less than,
Employees know that.
okay, so that's t-test is means, f-test is standard deviation or variance, chi-squared. I once taught at this class with a guy named Kai, and whenever the answer was chi-squared, I pointed at him. And he didn't quite get it until the end.
Oh my God.
And then I actually had a guy whose last name was Kai as well. And I wanted to introduce them so I actually could get chi-squared.
So are you gonna only remember me because in Croatian my name is something bad? You said that my name means something very bad in different language.
I don't know. So chi-squared. Chi-squared is goodness of fit. So chi-squared allows you to answer the question of how well does my mathematical description of a reality match with reality? So it allows you to test, does my data follow a normal distribution, an exponential distribution, a gamma distribution, a Weibull distribution? How well does my regression equation fit my data? Those are all types of questions you can answer with the chi-squared test. So that's chi-squared. And ANOVA is not only a show on PBS.
Is it?
NOVA? You've never watched it?
Mhm.
I never watched it.
Is this connected somehow to this F distribution?
Yes, believe it or not, ANOVA uses the F distribution. So what ANOVA is a hypothesis test for 2 or more means. So it allows you to compare sample 1 to sample 2 to sample 3 to sample 4 to sample 5 and say, are these means the same? We will potentially use ANOVA to answer the question of, is a Subway foot-long sandwich from the Subway in West Windsor the same length as the Subway in Neptune, as the Subway in Camden?
So what's the difference between hypothesis test for means, that is the T, and then the ANOVA?
Oh, we'll spend a lot of time on that. So the key difference, one of the key differences, there's 2 key differences that you should be familiar with between the difference between the t-test and ANOVA. In the t-test, you compare up to 2 things. You can compare 1 thing to a standard or 2 things to a standard. You can't do more than 2. But with the t-test, you can get directionality. So you can say, is A greater than B? Is A less than B? You can do that with the t-test. ANOVA, on the other hand, allows you to test 2, 3, 4, 5, 6, 7, as many samples as you want to each other. But for the power of being able to do multiple samples, you lose directionality. So you can just say, is there a difference? Is there not a difference?
Okay.
But it allows you to look at multiple factors all at the same time, where in a t-test, you can only do it pairwise.
Samples and
Okay, so which is the answer?
factors.
Okay, so now that we've defined all of them, I ask you which is the answer, which is going to allow us to tell if our data follows a exponential distribution.
I thought T.
Chi-squared.
Chi-squared.
That's what I thought. But,
Yay!
but I will tell you why.
Mhm.
I looked how the exponential exactly.
That's how.
I didn't even read it.
I just thought it is
How
doing
the
too much.
exponential
It can
look
answer
on the-
most
on the
that
graph.
one
It's
there.
like
Okay,
that.
okay. That was not the right way to get the answer. The right way to get the answer was to identify what the question it was asking you and to be able to understand that chi-squared is the goodness of fit. It allows you to answer the question of how well does my mathematical description of reality agree with reality.
No, this is actually my stuff. I didn't know it.
I didn't print out the new slides yet because I don't think we're actually going to get to the deck that I sent out.
Yeah.
What did we do last week?
We took the exam. We started to go over some of the measurement stuff.
We did 6. There's actually the
Well,
6,
we did the one that's
7,
mislabeled as 7.
Mathematical what? What's that?
Does your mathematical model, your mathematical description of reality, how well does it actually jive or agree with reality?
That's a.
Chi-squared.
Oh, but
How
we're going to
well-
talk about this.
Oh, We're going to
so
spend
small.
an entire lesson going over hypothesis
So
tests.
that's why it's still
So we'll
not
wait. I
understand,
know
okay?
you
And then we're going to apply it. But hypothesis tests are a tough subject. And you'll get a nice decision tree that you can follow down. And if you look through the notes for tonight, you can see the
Yes.
control chart decision tree and how straightforward and easy it makes life.
Okay, fine.
Okay, we're up to question 5. Which of the following are appropriate for a quality engineer to use in qualifying a process that has variable data? So we're asking the question about which graph can we use for variable data. So the first is an IMR chart. That's an example of a control chart for continuous data. So that's a good one. A histogram.
Called AI.
Thank you.
And it's IMR chart. It's a type of control chart. It's one of the first control charts that we'll talk about when it comes to measuring individuals, and the MR stands for moving range. So it allows us to look at each individual data point and see how it moves relative to the next data point in a series. So that's the IMR chart. The next is a histogram. We know what the histogram is. That's the bar chart. Okay, so then we have a C chart. So a C chart is a type of control chart that is used for defects. So it's based on the Poisson distribution. The C chart is based upon the Poisson distribution, which is really fun to say. And it allows us to look at counts of things. So how many people walk into Starbucks? You would use a C chart. Or how many scratches does a car fender have when it's coming off the manufacturing line? You would use a C chart. So that's the C chart. A P chart is a control chart used for defectives. It's based upon the binomial distribution. It's used for things that either are or are not. Go, no go, pass, fail. Conforms, doesn't conform. So that's the P chart. Okay, so the IMR chart is used for individual data, individual continuous data. Histograms, we know what those are. The C chart is used for attributes, particular types of attributes that are count type, 1, 2, 3, 4, 5, 6. And then we have the P chart that's used for the case of a binomial distribution, go, no go, pass, fail. So now that we've defined what each one of these things are, what's the answer?
I got B.
I got B2.
1, 2, and 4.
Okay, well, 3 and 4 are for attributes.
4 also?
Yes.
Okay.
Yeah, because it's either no go, no go.
I did 1 and 2 first, and then
Yep. So the answer is 1 and 2.
okay.
So a histogram can be used on continuous data and on discrete data. You can set your buckets to be continuous based on a continuous bucket.
A?
A is correct. So it's 1 and 2
Sure.
Histogram can be used.
on both continuous and attribute data. The IMR chart can only be used on continuous data. The P chart is used on attribute data, a particular type of attribute data being defective. And the C chart is used for attributes, and it's used on a particular type of attributes that's for counts, 1, 2, 3, 4, 5, 6.
I still don't understand.
Okay.
Because I thought A, 2, and 4 kind of make sense.
Okay, 4 is
I
wrong.
kind of read about this control charts, the first one, and was like, I said, I will use this.
Yep.
So I knew it was A or D. But
Yeah.
then I couldn't see myself without the histogram.
Okay.
But
Histogram,
then I was thinking, okay, one of these charts must be useful.
they're all useful. The issue is it useful for variable data? So this was questioning on which type of chart do you use for attribute data and which do you use for variable data. So C, U, NP, and P are used for attributes. IMR, XBAR R, and XBAR S are used for continuous. And if you look into today's slides, you'll see that broken out for you in that nice little decision tree.
So for variable data, which charts
IMR, XBAR R,
are?
yeah, IMR,
Uh-huh.
XBAR R, and XBAR S are used for continuous.
Can you repeat that?
Yep, IMR, XBAR R, and XBAR S are used for continuous.
So since 4 and 5 are not listed, then you said only 1 and 2 because you must look at the histogram and you must look at the first one.
I'm saying those two are correct. The C and P charts are used for attributes. So for attribute data, there's 4 types of chart. There's 4 types of control charts: the C chart and the U chart, and the P and the NP.
Are we gonna do these charts?
Absolutely, they're on the. Yep,
That's
that was in the deck that I sent out today.
Yeah.
C-U-P?
C, U, P, and NP. They are in the deck that I sent out today, which we probably won't get to. We'll probably start next class with the deck that goes through those.
Yeah. lot of charts which I really want to know which one is
Absolutely.
which one and why it's for this.
Absolutely. And if you looked ahead to today's slides, you see that lovely decision tree.
This
And
one I just kind of guess.
yep, and that's
By
fine.
elimination.
I had
It
first
will work.
one correct and then I went to the,
I just knew,
I just circled it here and I'm like, no. this-
Yeah. Question. Okay, let's move on to question 6.
Okay.
The correlation coefficient for a length and weight of units made by a process is determined to be 0.27. If the process were adjusted to reduce the weight of each unit by 0.5 ounces, the correlation coefficient of length and weight of the units made by the new process would be equal to. The answer here is 0.27.
Mhm.
Okay, explain please.
The correlation coefficient, it defines the relationship between one variable and another.
Mhm.
So that relationship isn't going to change because you reduce one. It's a constant.
Oh.
So if you're looking at the so you can think about it as density. The density of something at 5 pounds is going to be the same density at 2 pounds. It's a physical property of the relationship. So the answer there is B, 0.27.
If one changes, other changes.
Exactly.
But if the coefficient, correlation coefficient changes, that means one of the variables.
Yeah, it means that there's something else going on, that the relationship between the variables changed, yes. 7. 7 is a thing I don't like.
Okay.
7, a form in either a diagram or table format that is prepared in advance for recording data is known as a,
I said
I
first
have B.
A, but then D,
I
check
have
sheet.
yes, the answer here is D, a
D.
check sheet.
Mhm.
A check sheet is used to collect data.
Not checklist, there's a good definition.
Correct.
Yeah,
I-
I found it in the book.
Yes. you
Yes.
all read, huh?
So a cause and effect diagram, that's that brainstorming tool, also
Ishikawa.
called an Ishikawa diagram that allows us to come up with and identify what the root causes of a particular malady are.
Mhm.
So that's the fishbone diagram. The Pareto chart, we know what that is. That's that ranked histogram where we look for the 80-20 cutoff point.
Mhm.
So it allows us to identify where to focus our resources and allows us to limit or really identify the critical few from the trivially many.
Today I was reading very interesting article about this, and there was something about networking. If you want to network, you have you kind of pool,
Mhm.
and you use this 80-20, and you focus on this 20, the closest relationship, and then you solve those 80. You have no time. So
Yep.
It was very cool.
Yeah, the 80-20 concept appears and pops up in a lot of different things for no particular reason other than it does. It's sort of one of those interesting phenomenon. Flowcharts, we've talked about those. That's sort of a method of process mapping, a graphical depiction of what's going on in your process. And check sheets are a thing that is used to collect data. I don't like them.
Mhm.
I think they are muda, but we'll get to that later on. Okay, so the answer there was D, check sheet.
So Pareto charts basically what step of the it's not it's process improvement step
Yeah,
or
well,
an analysis step.
It's in the measure. It's in the measure and analyze phase. So you'll have some data and you'll start to analyze your data and you'll try to figure out where you're going to focus your resources on.
I think this is sometimes confusing because a lot of these things can be used in. Do they have questions like that? Where would you?
Yes, but there'll be the
Clear-cut ones.
more clear ones. They won't ask like when can you do an FMEA because the
Okay.
answer would be every
all
step.
the time, yeah.
No, but they'll ask you like they'll ask you if you should do a design of experiments in the define phase. No, you can't do a design of experiments in the define phase because you don't have any data yet.
Okay.
But the partition between what's measured and what's analyzed, they tend to be iterative. So
Yeah.
you collect some data, you analyze it, and you have to collect some more
Collect
data.
More data.
Yeah.
Yeah.
Welcome.
Hi. How's everyone doing?
Good.
Okay, we're just going over the exam. We're up to number 8. A major drawback of using histograms in process control is they.
Hey.
Hey, yes, they do not account for time. So we can look at the other ones. Are relatively difficult to construct and interpret. No, you learn how to make a histogram like in 3rd grade.
Oh, you have to ask questions.
Uh,
I just give it to you.
I'm sorry.
Do you have exam? He
No, that's
doesn't
the
have a
first one.
copy.
I think that I have another copy.
Okay. One of your classmates will hopefully bail you out. If not, I can print you one at the break. C, require too many data points? No, you can make a histogram with 1 data point. It probably isn't going to be the most helpful thing in the world, but you can absolutely do that. And D, require too many intervals? No, you can have 1 interval and make a histogram. It might not be the most useful, but again, you can create it. So our answer there is A. Does not account for the factor of time. I can talk. I really can. 9. Which of the following tools would be the greatest use for finding the most efficient path and a realistic schedule for the completion of a project? B. Yes, the activity network diagram.
B.
B. Boy, burritos.
Muy bien.
So the interrelation diagram, that's a brainstorming tool that allows us to look at the relationship and the connection between ideas. The activity network diagram, which was the answer, allows us to look at what tasks are being performed in parallel, what tasks are being performed in series. The tree.
It's easy to select the question when we do this activity. It's just really easy to.
That's why we do the activities.
Yeah.
The tree diagram. The tree diagram is that brainstorming tool that allows you to take a complicated project and make it into smaller, more manageable pieces. The affinity diagram, that's the thing that's brought to you by 3M, where you put the ideas in the Post-it notes, you stick them up on the board, you mush them around, and then you group them by some sort of categorical relationship, and you make the header card that describes that categorical relationship. And you guys made one of those, so you should remember it. Okay, so that was all the answers there. So now going up to question 10. A control plan is designed to do which of the following?
D.
I have seen.
Type D.
C.
Provide
I
a
found
method for
C.
tracking the design review. Provide a document system for.
Okay, this is actually an English question, and you guys way overthought it.
I said C.
And you're right.
Okay.
A control plan is used to provide a documented system for controlling the process. It's that easy. A control plan is used to control the process.
Okay.
It's that easy. You overthought it.
Okay.
It happens.
I was reading in the book, they were talking about the engineering plans and, you know.
You overthought it. Overthought it.
Okay.
11. To determine the average number of non-conforming parts over time, which of the following control charts would you use?
But if you think, I'm sorry,
Yep.
if you go back to the 10th question,
Mhm.
D is a subset of, is refinement of C, provide a documented system for controlling process. And then you look at D, it's a method of tracking the design review process.
Yeah,
It's-
well, the design review is generally done on the front side when you're first designing a new thing and you're going through bringing it into implementation. The control plans are different. So control plans are the output of the C in DMAIC. So you've done your continuous improvement project, and the control plan is how you know that the improvement's going to stick. Once the continuous improvement team has left, it's not going to backslide to where it was. So you've got those 20 pounds off. How are you going to make sure you don't put them 20 pounds back on 6 months from now?
Okay.
That's what your control plan is.
That is C. Okay, and then provide a method for tracking the design review process. This you think
Is more in the define phase, or in a non-Six Sigma project, in a design for Six Sigma project where you're developing something new from the start.
Okay.
Okay, so now we're up to 11. To determine the average number of non-conforming parts over time, which of the following attribute control charts would be most appropriate?
I think P. P chart. So C.
I did D, U chart.
Me
There was
too.
something about non-conforming. I don't
But it's
have
the
those
average, the one.
Average number of non-conforming.
notes. Those non-conforming something, the keyword.
You are correct.
But then I
Non-conforming
didn't
is the
have good
keyword.
notes. I didn't have good notes.
So we didn't get there yet. So non-conforming is the keyword. So non-conforming corresponds to defectives. So that means we're going with the P or the NP chart.
Exactly. That's why my notes. So that's why I select P.
Okay.
So the number is the NP. So the N in NP stands for number. The P is proportion.
Okay,
Okay,
we need
so
to go
where
over
We're gonna, that's what we're doing next class.
the average number of non-conforming parts over time.
11.
Which of the
I
following?
thought that
So
when they
because it's,
said
over
the average
time.
number of
So NP
non-conforming,
means
it was the U.
numbers. Yes, numbers.
I thought
Something. What is it?
I
NP?
could check my,
Right here. Number and proportion.
Number.
That's what I had.
but I had my previous notes
There
too.
was this the
Okay.
same question in the first.
The U was for the average.
And you said U chart for defects,
Defects.
variable opportunity chart.
Yeah, what I'm saying is defects. So defects are count type stuff.
So is
The
this
keyword
an
is not-
attribute?
Yeah, both the C, U, and the NP are attribute charts. The difference are what type of attribute are you measuring? Are you measuring conforming, non-conforming? That's going to be the PNP. If you're doing how accounts 1, 2, 3, 4 things that how many customers come into the store in an hour time period, how many scrapes are on a particular unit, that would be a C or U chart. But when you're dealing with conforming, non-conforming, that's the PNP.
And what's the difference then between P and P? The P
And
is,
B,
P is the proportion, so what percent defective you have, and NP is the number of bad units,
number of what?
number of non-conforming units.
that's where I get thrown off because C and U you said are for number of the
It's what the underlying measurement is.
What?
If the underlying measurement can either conform or non-conform, it is a P or NP chart. So let's talk about my car. So my car either starts in the morning or it doesn't, right?
This is number
If it doesn't start, it's non-conforming. If it starts, it's conforming, right? My car has lots and lots and lots and lots of scrapes and dents in it, right? Remember, it's the same car I've been driving since high school and it's got 309,000 miles on it. So each one of the scrapes, dents, and dings is an example of a defect. It has lots and lots and lots of defects in it, but it's not defective because when I turn the key, it starts and I can drive and put 100,000 more miles on it and not get a date. God's not going to help me get a date, and it's not going to help you pass the exam.
I know.
You've got more important things to deal with.
We have to go.
We're going to go through it, and it's in the slides. There's an entire decision tree that you got. It's there. I think it's on like page 3 of the slide of the real Deck 7, not the one that's labeled Deck 7
Today?
tonight's. We're probably not going to get to it because we're a little bit behind. That's a bit of
See, I think, I'm sorry, I'm
Yep.
just stuck on it. It's non-conforming parts, but it's also saying to determine the average number
Mhm.
of non-conforming
Yep,
parts.
exactly. So what that's drilling you in on is the P versus NP distinction. So,
Example about P and example again about NP.
okay,
Yeah,
I had that note. in
yeah.
you.
we'll spend a lot of time going on this,
Yeah,
but here's the key concept that if I say I got 90, if I say to you I got 35 questions right on this exam or on an exam,
Number.
yes, right? Or I say I got a 70, 70%. Those things, if you know how many questions there were on the exam, mean the same thing. However, if I say I got 35 questions right on an exam that has 50 questions, and then you take the final exam that has 100 questions, and you say you got 35 right, those aren't the same thing. Right? So in one case, you got 70% right. In the other case, you got 35% right, because our opportunity size went from being 50 to 100. So if you're just looking at the number of right answers, it wouldn't show you a difference, 35 and 35. But if you looked at the P chart, the percentage, the proportion, you would see 70, 35. And if you don't get it the first couple times, that's what we're going to spend all of the first half of next class going over.
Okay.
Okay, another 12. Which of the following techniques is most appropriate for generating continuous improvement ideas?
Be brainstorming.
Yes, and this is a good test-taking strategy question because you see tree diagram is given, and so is brainstorming. Tree diagram is a form of brainstorming. Therefore, since brainstorming is broader, it's a better answer.
But how is this the continuous improvement idea?
Yeah, it's all about coming up with ideas.
The brainstorming you do initially at the beginning.
Yeah, to generate the ideas.
It's not continuous improvement. You
That's-
start with the project and you brainstorming.
Yep.
And later you kind of. I'm reading the question and I want to answer the question.
Yeah, generating continuous improvement ideas. How do you come up with ideas? You brainstorm.
See, you
You overthought
overread
it.
the last one we did. This one
Yep, you overread it.
because we were like number of.
I think that's the issue though, because that's what I remember with the CQA. I feel like you're trying over.
Yep, just read what the question
I
says.
just want to read it and understand what is the.
Okay, so we can go through. Let's go through each one of these because they're sort of important. So tree diagram, we talked about complicated problem into more manageable, smaller problems. Brainstorming is generally this idea of coming up with ideas. Prioritization matrix, well, that's a way, like in the House of Quality, where you're looking at how to rank ideas relative to each other. Interrelation diagram, again, that's that brainstorming tool that allows you to look at the relationship between ideas. So again, an interrelation diagram is a form of brainstorming, which makes brainstorming a more correct answer because it encompasses tree diagram, it encompasses interrelation diagram, it encompasses the force field analysis, the Ishikawa diagram, all of those things we talked about during the second class.
She's generating ideas.
C was not good answer because C is what?
Ranking ideas. It's not coming. It's not creating the ideas in the first place. It's ranking them. It's prioritizing them. Did we skip one? No, 15. Which of the following tools would be most appropriate for collecting data?
13.
13. I did skip one. I'm sorry.
Yeah.
I thought I did.
Clean.
This one?
No,
Yes.
Okay. Which of the following tools is used extensively in the QFD?
I said B.
Yes.
Ooh, I love what.
Neo-
If I see matrix, I always like.
Neo and Morpheus and Trinity would be very proud. Someone got it! Yay!
What?
I said Neo, Morpheus, and Trinity would be very proud of that answer.
Yeah, it's like
Is it B or no?
Yes, the answer is B. That's why we're talking about the Matrix.
Matrix.
this number.
It took me 3 times to watch the movie and get it.
I know.
I know. My husband and my son would rave about the movie. I said, what did I do?
You don't get it.
Have you said anything about matrix diagram before?
Yeah, we use it in the QFD, the quality functional deployment. So that shows the relationship, the connection between multiple ideas. Yep. It's in the QFD deck.
So that 11th one that you did, what was the right answer? Was P or NP?
NP.
NP.
Yes, exactly. 14. Which of the following tools is most likely to be used to organize a list of ideas generated during brainstorming?
Affinity diagram.
Yeah.
Woohoo!
You all got it.
I know something.
15. Which of the following tools would be most appropriate for collecting data to study the symptoms of a problem?
Force
said
field
C.
analysis. I said C.
Collect data. Where do you collect data?
D.
Where do you collect data? It was a question. Check sheet. Yeah, there you go.
For collecting data. Oh, collecting data to study the symptoms. See, I got.
Where do you collect data
But I
on?
have
You,
to say as you, the C.
you collect data on a check sheet.
But
Flow
the
dot.
force field also says.
No data.
the
No data.
symptoms.
No data.
I-
No data. The
Wait.
force field is a brainstorming tool that lists out the driving forces and the
But
restraining forces.
that's like we
That's what I
capture the driving force and what the problem is and what are the symptoms.
Data.
Collection.
Yeah.
Data.
And I only read symptoms of the
No
problem.
Data.
Okay, we got it.
Check sheet.
16.
Guys, and continuous
16
improvement.
C. Everybody knows.
Yes. 17. 17 is actually one of my favorite questions.
Interesting question.
17 is one of my favorite questions on the entire exam. And this is an example of one of the circumstances where the green belt and the black belt body of knowledge overlap. So this is on the harder side of the green belt questions and is on the easier side of the black belt questions. So if you drew the overlapping distributions, this would be in both.
So
Because
I
this is a thinking question.
Oh, thank you.
This requires some thinking.
So I looked at it, okay, from my 80-20 rule.
Nope, you're not going to get to that.
Wrong. Okay, then I should keep that.
Okay, so let's look at the question. A legal requirement specifies that a bottled product must contain no less than a volume printed on the label. This is actually true. In New Jersey, it's $100 per unit. A bottling company wants to reduce the amount of overfilled bottles. Okay, so they want to reduce the amount of waste money they're putting out the door, and they don't want to trigger their legal requirement. So what should they do? So let's look at the different options, right? So if we decrease the target fill volume, what happens? Yeah, and we're now producing units below or lower spec. That's not allowed.
No,
Not an
that's
option.
not.
Decrease the target fill variation. So we're going to decrease the width of our curve.
That's
Have we saved our company any money? No. First, decrease the target fill volume, then decrease the target variation.
no.
We got a problem still. First, decrease the target fill variation, then decrease the target fill volume.
Oh, I'm sorry, I have to take back. I didn't apply the 80-20 here. There was another diagram where I applied this one. I
Okay.
got lost.
Does everyone understand
I
what
got the
it is?
answer right.
Okay, so the idea is,
Can you tell him the story about Pepsi? I got it.
Okay.
Yeah,
about
because
that story.
so in
I got the
in
background.
New Jersey, if you have a printed value on a bag of chips and it says there's 16 ounces in there, if a consumer finds there being 15 ounces in that bag of chips, it's a $100 fine per unit to Frito-Lay.
Way more stuff.
So the manufacturers will make it such that the probability of finding a bag of chips with less than 16 ounces is essentially zero, because the penalties are so high.
So the variation is less.
So they'll deliberately overfill their product to make sure that the probability of the consumer getting a product that is less than that amount is basically zero. So, but every free chip Frito-Lay puts in the bag is money out the door. So they want to have the variation be as small as possible, but to make it show that the likelihood of a consumer getting a bag of chips without that 16 ounces is as unlikely as possible. So what this problem is describing is, what should Frito-Lay do? If Frito-Lay first just decreases the average amount that they put into a bag, well, they're going to have bags of chips that are going to be less than their legal requirement. They're going to be liable for a $100 per unit fine, which adds up really quick when you think about how many bags of chips Frito-Lay sells. So that's our option A, decrease the target fill volume. So that's going to trigger that's going to be below the legal requirements. That's going to be bad. So we can go to option B, which is just decrease the variation. So variation is how fat or thin the curve is. So if we make the curve thinner, we haven't saved them any money, because we're still overfilling every bag. So that's a better option than A, but it's still not doing what we want. So we can then look at option C, which is first decrease the target fill volume, then decrease the variation. Well, as soon as we decrease the target fill volume, we're below our legal requirement and we got problems. So that can't be our answer. So then we have option D, which is first decrease the target fill variation, then the volume. So if we decrease the variation, that's good. And then we decrease the volume, we're really good, because we haven't dropped below our legal requirement and we've saved Frito-Lay some money.
When you buy medication and it says tablet, there is 100. It's never 99.101. I remember that.
Yeah, we'll talk about my experience in making with. Oh, can I tell that story? Can I tell a cool story that's somewhat tangentially related, but I like it?
Yeah.
Can I tell a somewhat tangentially related story? I like this one. Okay, so generally, if in most consumer goods and most things in general, if you pay for a pound of turkey at the deli and they give you a pound and a quarter, you generally don't complain, right? You go to Dunkin' Donuts and you order a dozen donuts and the guy gives you a dozen donuts and hands you one to eat. You get 13 donuts, you're generally pretty happy, right? Mm-hmm. Unless you're on a diet, but we get the idea. So if you buy a dozen screws and there happens to be a 13th screw in there, you generally don't bitch. So I was contracted for a contract manufacturer that, well, we got a request. I wasn't contracted. We got a request for quotation from a contract manufacturer of plastic medical thingies. Basically, they make cheap surgical medical type components in a sterile lights-off factory. And this particular device was basically, there's no other way to describe it. It looked like a clothespin, a little clothespin. And they sell for their manufacturing cost is like $7 cents a piece. And I think they sold them for like $1 each. So not a really valuable thingy. And they needed a system that was 100% accurate to be able to pack these things out in packs of 10. 100%. And they wanted us to bid on it since we'd done some other work for them. And I basically said, no, we can't do it. We can't ever get to 100%. I can maybe give you 99%. I can't give you 100%. And we were there working on another project. I'm like, okay, I give up. These things are like 7 cents a piece. Who the hell cares if you give your customer an extra clip? They're 7 cents. Who cares? And he's like, oh, well, these little clothespinny things are used in brain surgery. And the surgeon knows there's, 10 in a pack. If for whatever reason there's 9 in a pack, the surgeon's going to do the surgery and then go to close up, and he's going to try to count out 10 clips. So if there's not a 10th clip, he's going to go poking around in the person's brain looking for the missing clip. So that's bad. Also bad, if there would happen to be 11 clips in the bag, the surgeon's done the surgery, counts out his 10 10 clips or her 10 clips and leaves the extra clip hanging out in that person's brain.
They always count how many.
They're supposed to count in and count out.
Everything, yeah.
They're supposed to count in and count out, but in a surgical environment, I hope the surgeon's got more important things to be worrying about necessarily than counting the number of little plastic 7-cent clips.
I think it's very critical in surgery.
Yeah.
Yeah.
There's enough people there counting, but I would like my surgeon to be focused on like actually doing the surgery.
I don't want him to be leaving anything more
I-
or less inside my brain.
Well,
No, I better count.
but generally in consumer life, we generally don't complain if we're given more than we ask
Yeah.
for. And that's why the legal requirements are set on most consumer goods is that they set a minimum requirement and not a maximum. It's a one-sided spec limit. That's why I like this question. I think it's pretty realistic. 18. Which of the following tools is commonly used to define, used in the define phase of a project?
I have C.
I have A.
If you put C, I'm sympathetic because an FMEA, because an FMEA realistically can be used in every step of the process and will be used in every step of the process.
Yeah, I put A.
The answer is A.
Affinity diagram.
The answer is A because the affinity diagram is exclusively used in define, where an FMEA can be used in define, it can be used in measure, it can be used in analyze, and will absolutely.
I was also confused between data collection checklist.
Yep. Yeah, so data collection is used when you collect data. And where do you collect data? In the measure phase.
Measure phase.
Yep.
Yeah, that's right.
And control charts are used in the measure and the analyze phase because you have the data, you're going to look at the data, you can use the data to draw some conclusions. That's where the control charts come in. So control charts will be in the measure and analyze.
The theta is going to be measured, or
The C is going to be at all stages. It's not going to be unique to a particular stage in DMAIC. And data collection checklist, as we said, you need the data. So data comes in the measure and the analyze phase. No. 19. The least informative of the 4 measurement scales. Well, we had just gone over this.
Nominal.
Yes, no.
Okay, good.
Because just going through these, ratio. Ratio is a measurement scale where there's a rational 0, where 0 represents the absence of the quantity. So 0 grams means there's no weight, there's no mass on the scale. Nominal. Nominal groups things into categories. Red, green, blue, men, women, pass, fail. That's nominal. Ordinal. Ordinal puts things into order. First, second, third, fourth, fifth. So the first part off the line versus the last part off the line. Those are ordinal. Likert scales. There's lovely, I agree, I somewhat agree, neutral, somewhat disagree, disagree. Those are examples of ordinal measurements. Then you have interval. So interval is closely related to ratio, and it is a measurement scale where the increments represent the same amount of physical property. So to go from 10 to 20 represents the same change in the physical property as going from 10 to 20, or 110 to 120. All increments have the same scale. Cool. So now we're up to 20. Which of the following can be used to determine the goodness of fit of a distribution to a data set?
I now know it.
Yes, and that's the important part. The answer is chi-squared. So the t-test, as we talked about, is a hypothesis test for means. ANOVA is another hypothesis test for means, which allows us to test 2 or more samples. F-test is for standard deviation and variance. And chi-squared is for goodness of fit. 21. 21's our first math question. Remembering on the real exam, you will have up to 5 math questions. Yes, the pre-tests have a little bit more math than that.
Yeah, there was a lot.
No, there was not a lot.
Almost everyone.
That was not that much. Okay, 21. When sigma is 10, what sample size is needed to specify 95% confidence interval plus or minus 3 units from the mean? So what do we do? What'd you do?
Nothing. I just picked the question.
Well, what would be a good strategy? Well, perhaps you should look in the index for a confidence interval. So why don't we do that? Let's go look in the book for confidence interval. Open the book. To quote Finding Forrester, it might crack a little bit. You're not going to hurt it.
oh no.
I said no. I never said not to look in the book. I say to look in the book all the time. I like the book. So if you look in the index for confidence interval, Yes. Yes, have confidence in your ability to find it under confidence interval. There you go. Be confident.
Two nine.
292.
290 onwards. 290 onwards.
So like that.
I have 292.
Okay.
Is there a formula?
Interval
Confident.
Okay, what's the formula?
X
X bar plus minus
C.
plus minus Z
alpha over 2.
alpha 2 sigma square root of n.
Oh, you get it.
Wow. Okay, so this is sort of your procedure for how to go about answering math questions on the exam. The first is to identify the formula. So we did that.
Mhm.
The next step is to figure out what the problem is giving you.
Mhm,
Okay, so they're telling us that sigma equals 10.
mhm.
What else are they telling us?
95%.
They're telling us that our confidence level is 95%. So we should immediately know that if our confidence level is 95%, alpha is 0.05.
Oh.
Because 1 minus our confidence level is alpha.
Mhm.
Okay. What else do they tell us? They tell us that we want to know the confidence interval or plus or minus 3 units from the mean. So what is that telling us? Oh, we'll leave that off. We'll leave that off. Okay, so what else do we need to know? We need to know Z alpha over 2 for alpha being 0.05. Now this is something that you should write in the front cover of your book. Z alpha over 2, where alpha equals 0.05 equals 1.96.
Alpha over 2 equals.
For alpha equals 0.05 is 1.96. We'll talk where that comes from when we get to our hypothesis section, but just for now, know that Z alpha over 2, if alpha equals 0.05, is 1.96. So now we know Z alpha over 2, we know sigma, we don't know the square root of n. What else do we know? Well, we know, we want to know x bar plus minus 3 equals, right? That's what the problem wants us to know. And we know that that's going to equal x bar plus minus Z alpha over 2 sigma over square root of n, right?
Mhm.
Just going from what the formula and putting it together with what the problem was telling us. Ask me stop me if I haven't made sense, if I stop making sense.
Okay, and how much was n?
We have to solve for n. That's what we ultimately need to solve for. But all I did is I took what the problem told us that we want to know our confidence interval to be the mean plus or minus 3. And we know our formula for confidence interval is what we got from the book. So now if we just do some canceling, we get 3 equals 1.96 over 10 over the square root of n. So we just have to solve for n. So we get 3 over 1.96 equals 10 over the square root of n. So square root of n equals 10. You guys can do the math. So what's it come out to be? So that's 1.5. It's going to be 6.
19.6 divided by
So it's going to be
3 squared. 3, 6, 9, 6.2 squared.
So we should get something like 43.
Yeah. Guess what? I blindly said 43 because
Okay, did everyone follow?
How do you know?
That.
I didn't think like that. I thought very differently.
Okay, tell me how you
I
feel.
used the formula.
Okay, how did you use the formula? How'd you do it? Did you get the right answer? Okay, conceptually, all we did is we took what the formula told us. Well, first off, we found the formula. Then we took what the problem told us. So it told us that 10, told us confidence level was 95%. That allowed us to determine what Z alpha over 2 was.
But this one I don't know. So
Well, now you do.
Yeah, now I know.
And then all we did is some algebra. And we solved for n.
So what was the process thinking when you got 43?
Oh, we just solved for n. So,
I know, but I'm sorry, I forgot.
oh, what was your process? I don't. Let's not go with that one. The correct way to approach it is this way. What other machinations? Probably, if you look at the math and the steps you did, you probably got to the same result. You just might have gotten a different route. Obviously, you could have done the algebra in any which way, as long as you followed the algebraic rules. Okay, so they're moving right along. 22. And if the math is sort of looking Greek to you, that's fine. Remember, on the exam, there can be up to 5 math questions, so you can miss all of them and still pass. 22. Which of the following techniques would help increase process stability when the cause of variation is a cluttered workstation?
5S.
5S, yes. So let's go through each one of the options here because they're sort of important. So 5S are those 5 Japanese words starting with an S sound that have been translated to 5 English words that start with S, which in my experience are translated to 5 Spanish words that also happen to start with S.
So, sustain something.
Yeah. That's one of those lookup questions that I don't waste my time memorizing.
Yeah.
Okay, so they are the housekeeping ideas that are going to provide the foundation for lean. SMED, single minute exchange of dies, is the idea of quick changeovers from making one product to the next. At American Standard, our goal was to do single shift exchange of molds, such that we'd only lose one production run going from making one toilet to the next. We couldn't get there. We started from 3 shifts to change over from making one product to the next. SMED represents the idea of being able to do it in less than 1 minute.
What is it again? Single minute?
Single minute exchange of dies. So it's the idea that you can change over from making one product to the next in less than a minute.
Dies.
Yeah, dies, as in if you were using tool and die. So if you're stamping metal, is where it comes from. So that you could go from making a fender for a Toyota RAV4, and a minute later, on the same machine, make a fender for a Toyota Corolla. That's the idea of single minute exchange of dies. Preventative maintenance, well, we know what preventative maintenance is. Preventative maintenance is the idea of doing repairs, changing your oil type stuff.
So what does SMED really fall under? It falls under the same process, like.
SMED is one of the, it's one of the things that it's a goal, it's an ideal. It's in focus area. So obviously changeover time is waste.
So it's a lean theory?
It's a lean theory, yeah.
Single minute exchange.
Yep.
Minute.
Preventative maintenance, we know what that is.
Single
And
minute exchange of dies.
Yep.
Single minute exchange of dies.
And then we have visual factory. So visual factory is this whole idea that we've talked a little bit about making things visual. So making it such that anyone walking onto your production floor can know how you're doing on that day. It's your scoreboard. It's because just the natural inclination is that you play very differently when you're behind than when you're ahead. It's
There's
very
another Japanese term for that visual, right?
Pokyuki is mistake proofing. There's Kanbans, that's the signaling. That Kanbans come into our component of visual factory.
Okay.
But when it comes to the visual factory, it's the whole idea of allowing anyone to walk into your factory and know what the hell is going on. Are we winning today? Are we losing today?
Is it possible?
Yes, it's actually done very well. Zodiac Air Cruisers does a very good job of that. Walking onto their production floor, you basically get we're winning, we're losing today. Okay, so that goes through all 22. 23. A process capability analysis is not used to. Okay, so this is an example of a negative question call. Fortunately, on the exam, these have been eliminated. But for your fun and enjoyment on the practice test, we still have them.
I said A.
Okay, the answer here is B, as in boy, or burritos. And this is a very important concept. Process capability can only be assessed once your process is in control. If your process is not in control, you cannot do a process capability study. Because if your process is not stable, you can't make predictions. And what process capability is all about making predictions. It's all about being able to predict the likelihood of providing a good or delivering a service that meets or exceeds your customer expectations. So if my process isn't predictable, I can't make predictions. That's the whole idea. So you can't maintain your process in statistical control by doing process capability. You can't even do process capability if your process is not in statistical control. The exam will try to trip you up every which way on the differences between spec limits and control limits and when you can do process capability. So we'll go through those a lot when we get, actually that'll probably be in the second half of today. We'll spend some time talking about that.
What was the answer?
The answer was maintain a process in a state of statistical control.
Process capability analysis.
So-
is not used to maintain a process.
So it is used to determine the ability of a process to meet specifications. That's exactly what process capability is used for, is to answer that very question. Establish new specifications. Yeah, that's very reasonable. My ability to produce a product, yeah, absolutely, that seems very reasonable. And prioritizing competing processes, absolutely. You should focus your improvement efforts on processes that are less capable and try to bring them up. Okay, so we're up to 24. A line graph used to assess. Yep,
So
that's
for
fine.
23, the process capability analysis is not used, and the answer is B, because that has to happen before you can write. Okay.
Precisely. Precisely. Before you can do a process capability analysis, your process must be in a state of statistical control. 24. A type of line graph used to assess the stability of a process is called a,
I said control chart.
and you would be correct.
Yay.
Yes, a control chart is a tool that allows us to determine the extent of our common cause variation from our special cause variation. It allows us to determine that variation that we're likely to see from the variation that we're unlikely to see.
Mhm.
Pareto chart, we know what that is. That's that ranked histogram. Then the check sheets, that's where we collect our data. And finally, the cause and effect diagram, that's the brainstorming tool that allows us to identify why I don't have a girlfriend. That was a delayed reaction. 25, we're halfway there. Oops. A process produces nonconformities according to the Poisson distribution. If the mean of the nonconformities is 25, what is the standard deviation?
B.
Well, if you looked in today's slides, you'd actually see it.
It says if mean and variance for Poisson distribution is the same.
It's the same. Okay.
It's on our slide.
Yes, it is on the slides for today, actually. Well, for yesterday.
And also in the book, the table. is
Yeah, there's a
behind.
table in the book too. So in the Poisson
Right.
distribution, the Poisson distribution has a very special concept of that the mean and the variance are the same value. So if the mean is 25, that means the variance is also 25.
25.
But the question is asking us about the standard deviation. And what's the relationship between the standard deviation and the variance? The standard deviation is the square root of the variance. So our answer is 5.
5. Yeah, I just stopped, I think.
You stopped, you're like, oh, I'm all excited. I found for the Poisson distribution the relationship between the mean and the variance, and you thought you were done. But the question wasn't asking you about the variance, it was asking you about the standard deviation.
Standard
You got close.
But yeah, I
That's okay.
remember now for good.
That's why we go over it. Okay. Now we're up to a question that I doubt any of you got right. And actually, when you see this on the real exam, I hope you get it right. So let's read it. 26. 5 six-sided dice are rolled together 100 times. 2 histograms are constructed. One for the 500 individual results and one for the 100 averages of the 5 results. In this situation, the average results follow a uniform distribution while the averages follow which of the following distributions?
I just made a blind guess. I said C.
The answer is A.
Wow. Good for you.
And this is about the central limit theorem.
Okay.
So we will spend a bit of time in our hypothesis test section talking about the central limit theorem. But the idea with the central limit theorem is regardless of what the shape of the underlying distribution is, if I sample from that distribution and I average my samples, so I take a first sample from my distribution, I average it, I plot it, take a second sample, average it, and plot it, those plots of averages will follow the normal distribution.
Okay, say that again. If the
Where that is right.
Okay, so if I have a unknown distribution and I take a sample, I take 20 pieces and I average the mean, I calculate the mean, the average. I calculate my first value, I plot it. I then take a second sample. I take that mean and I plot it. And I do that a lot. Those means, the plot of the means will follow a normal distribution.
but you said the first distribution is unknown.
No, unknown. It could be normal. It could be normal. It could be, in this case, it's uniform. It could be Poisson. It could be gamma. It could be a mixture of distributions.
So it's basically what you plot is the averages of means. That's why. Or-
Mhm. Exactly. Precisely. Yes.
Individual results was the case.
Yes. The individual results will follow the uniform distribution, right? The likelihood of rolling a 1, 2, 3, 4, or 5, or 6 on a die is what? The probability of rolling a 1 is what? 1 over 6. What's the probability of rolling a 7 on a single dice?
0.
Exactly. So the probability of drawing 1, 2, 3, 4, 5, and a 6 all have the same probability, so that's a uniform distribution. So this question is asking about the averages of those, and those averages will follow a normal distribution.
So uniform distribution is. Could you just?
We'll get there today.
Okay, so you. will
Coming
have-
attraction, that's actually in the second half of today's
What
class.
is the student's ST?
The
This is-
students, that should just be, I don't know why there's a space there. It's the student's T.
Okay, student's T.
The student's T distribution is a lot like normal distribution, and actually it converges to the normal distribution as your sample size becomes very large. So the student T distribution is used for small samples. It's the normal distribution with fatter tails, basically.
But you'll talk about.
Oh,
this
absolutely.
because This is.
It's the whole thing is, and see how it's labeled probability, the first thing is labeled distributions? That's what we're gonna talk about. Okay, so the answer there was normal, because of the central limit theorem. Okay, 27. Yeah, a calibrated micrometer is used to take 10 replicated measurements in a reference mean of 73,000. And if the true value of the reference standard is 75,000, so what is the bias? So remembering we talked about bias is the difference between the true value and the observed value. So the answer there is B. Yes. 28. The power of a test for differences between means. So power is defined as 1 minus beta. So our answer is 1 minus beta. So alpha is our level of significance, 1 minus alpha is our confidence level, and beta is the probability of a type 2 error.
What was the
Which
answer
one?
for 27?
One more time, 28. B. B 1 minus alpha?
Okay, alpha is. I want to.
Hang on. We'll
Exactly.
two questions going on at once. The answer to 27 was
It's
B,
in the-
2000s.
True value
I found
minus
that very
measure.
confusing.
Okay, so now let's go through each one of these pretty slowly. Alpha. Alpha is your level of significance.
Mhm.
Alpha is your level of significance,
Type 1.
which corresponds to the probability of a type 1 error. Correct. That's alpha. 28 for question B, option B. 1 minus alpha. 1 minus alpha is your confidence level. 1 minus alpha is your confidence level.
Okay, 280.
Beta. Beta is the probability of a type 2 error.
Yeah.
And 1 minus beta is the power of your statistical test.
In the page 280, in the note
280.
280 says P is equal 1 minus
Oh my
beta
God.
is also called power.
How come you let go of everything in color?
Because she highlighted it.
She went through. I'm lying.
She couldn't fall asleep. Or she was flying back and forth to
Or
Puerto
maybe she
Rico.
has a lot of highlights.
No, I think she was
Oh.
flying back to Puerto Rico and really couldn't fall asleep and needed something to read, so she read this.
You're right, sure.
Okay, cool. Page 140. Now I'm gonna highlight it.
Okay, so
I think I got one of them.
we defined all four of those. So the answer there was D, 1 minus beta, because that is the question's asking us to define power. Now we're up to 29. A process is stable and its output is normally distributed. The process has a spec of 16.73 plus or minus 100.
Mhm.
What is the maximum process standard deviation if CP must equal greater than 1.5? So our first question is to figure out what the formula is for CP.
Is tolerance over 6 sigma, right?
Mm,
Oh, 6, not 6 sigmas.
I don't know. I just
Yeah, 6.
Okay, so CP, what does CP equal? It equals the upper specification
Should-
limit
but
minus the lower
That's like
specification limit.
tolerance, right?
Yep, tolerance range
6.
over 6 sigma.
Yeah.
Okay, did we find that in the book?
Mm-hmm.
It was hiding in the book?
You told us, and we found it in the book too.
It's hiding in the book somewhere.
In what
Yeah.
page?
I think it's on page 128,
Okay.
128?
maybe. Yeah.
Okay, so what's the problem telling us? So they're telling us what the upper spec limit is.
Upper spec limit is
16.7?
16.74.
Our lower spec limit,
16.72. The difference is 0.02.
okay, are they telling us what sigma is?
Sigma,
Is question mark?
yeah.
CP is 1.5, right?
Mm-hmm.
Okay, so now we can start substituting in.
Mm-hmm.
16.74
8, yeah.
minus 16.72 over 6 sigma equals 1.5.
Mm-hmm.
So 0.02 over 9 equals sigma.
Mm-hmm.
So hopefully we get a bunch of repeating 2's. And our answer is B. Did I lose anyone with my crummy penmanship?
Is it the answer?
0.2. Yeah. What did I skip?
In question,
6
always
sigma.
mark B.
Yep. Okay. I did 2 steps at once. I apologize.
CP is 1.5, right?
Yep. So we have, just by doing the subtraction up top, we get over 6 sigma equals 1.5. So we multiply both sides by sigma. We got 0.02 equals 1.5 sigma over 6. And then we just divide by 1.5. So sigma equals 0.02 over 6 over
Okay, I know
1.5.
what I did wrong, yeah.
Yep, pesky algebra is always our friend. Okay, now we're up to, what are we up to? We're up to 30. Yes, I scrolled down too much.
Oh, sorry.
Yeah, but I'm bored. I
The
scrolled.
answer was B.
The answer was B, yes. According to Durag, when a major quality improvement project is launched, which of the following describes the desired change in the performance level?
6 sigma.
No,
Continuous.
no,
I have
No
a
continuous?
no,
Did you have?
no.
I have
Okay, you've guessed every answer besides the right one.
But you,
C.
C, yes. Okay, so this is
I
a,
remember you said it. That
Yep.
if you see the word
get rid of them, put yourself.
exact,
Exactly, and now let's put you into this process, and we'll figure out why this question's
Okay.
right. You are launching a project. Projects are expensive. You get continuous improvement. The idea of Kaizen is that you're going to get improvement just by being. You don't need to invest in it. That's the small incremental improvements you're going to get for free. When you're launching a project, you want something more than that. You're making a big investment, and you want a big return.
that's why.
It's breakthrough, yeah. You're going to get that for free just because of having a culture of continuous improvement. Sporadic, you don't want sporadic. That's bad. And then you have it down to 6 sigma and breakthrough. Well, Six Sigma is generally unobtainable. I will actually give you my lovely conference paper that I'm presenting in 2 weeks. That will bore you to sleep, but we actually show something that's over Six Sigma level, which is the probability of data overage on a 10 gigabyte plan based upon my data usage. Really exciting stuff. So the answer there is breakthrough. Because you're launching a project, you want more than just small improvements. You want there to be a big improvement. That's why you're launching the project. Okay, we're up to 31. Which of the following figures is labeled correctly? Okay.
B.
I said D.
Okay, so let's go through each one. So R gives us our directionality. So a positive R would be up and to the right. A negative R would be down and to the right. Okay, so is this negative R value? No, it's a positive R value, so that guy's gone. This guy, is this positive? No, it's 0.
It's
fine.
not changing.
It's not up or down. It's 0. So up and to the right is positive, down and to the right is negative, and nothing is 0. So that guy's wrong. Okay, so this guy, that's negative. He's wrong. R is positive. Okay, what's that guy? So we only have one that's labeled correctly. So that's our answer.
Yeah.
So let's look at R squared. So R squared is how closely our line matches our data. So the closer the dots are to the line, the higher the R squared value. Because R squared represents the percent of the variation in Y that is explained by X. So in this one, our R squared isn't 1. Not all the points are on that straight line. So that answer is the R squared is reasonable. It's not going to be equal to 1. It's going to be pretty high. Most of the points follow the line, but it's not going to be 1. B, all of our points are on the line, so R squared is going to be 1. But there's no that's so okay. C, R squared is about 0. Well, no. And D, all of our points are perfectly on the line. So there we go.
Fail.
Okay, so now we have 32, which is actually a question about Pareto charts. So a quality improvement team was assigned to decrease the number of pinholes in milk jugs and presented the following information. This guy. Okay, so the best way to interpret this is that the project was
D.
Yeah, so D is the answer. They were successful in decreasing pinholes. That's true because we can look at the magnitude. The magnitude has gone down. And the team should work on cause B to further improve the process. Exactly. Because B now became the top guy. Perfect. Moving right along, 33. Which of the following method is used to develop an exhaustive list of ideas about a subject?
I'm getting so scared in answering these answers because every brainstorming.
Yeah.
The one that look like easy ones, they're always
No. The easy ones are actually easy. 34. Oh, well, the main advantage of a matrix diagram is that it.
Okay, I have confusion with this one. I think it's B, but C also looks right, but B is the one because it's talking about the strength. That's what we remember, right?
Matrix diagram.
I had confusion
pair
between B and C.
combination. That's what I had.
But I ended up.
The answer
not-
is B, as in boy or
B, yeah.
burrito.
Right, because that QFD tells the positive, negative strength. But if you think about it, it also.
Does it classify?
Yeah, in a way, it does. Because you can see if the customers,
We have one.
yeah, the higher,
Because the sample that you
Yeah, I
presented
don't
to
know.
us,
it
you
probably,
continue adding other stuff, so you
So you
like
can get-
categorize
yeah.
things.
But I think that's a stretch.
Yeah, I think you're stretching it.
Yeah, so B. So
The answer is B. B is
C.
definitely a better answer.
Okay, good.
Probably if we stood here for 20 minutes, you could convince me that C is reasonable, but B is clearly the better answer.
So first, I think I have come down, the first gut instinct is what you have to go with.
Poke-yoke, 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 poke-yoke.
Reducing field failures to virtually 0.
0.
I have that one too.
B.
Poke-yoke is the whole idea of designing a defect out of the system. So this is why you don't accidentally undo a gas line when you're trying to undo a water line. One's a left-handed thread, one's a right-handed thread. It's why you
Not the field failure.
It's not
right? It's best to prevent controllable defects.
Yeah, that's what I'm saying.
Mhm.
It was in the book.
Mhm.
Yeah. I don't know where, but
I looked at the.
Yep.
I think in
So-
also your notes they have.
Yeah, my notes will say that it's error proofing, it's mistake proofing, it's designing out the mistake from it possibly happening. It's
Yeah,
making it so it doesn't fit.
Zero error.
Well, you're not going to get necessarily to zero error, particularly field failures, because what you're
I
going to
got
get controllable
this wrong.
defects. It's all about controllable defects. It's so why you can't put in the lovely HDMI connector in upside down because it's trapezoidal.
But it's not like trying to eliminate all the error almost to zero.
Well, it's field failures. Field failures are dealing with factors that you can't control.
yeah, that was when you explained it to us how you get the gasoline diesel and the other one.
Mhm.
That's what you said.
Yeah, the diesel
You
doesn't
cannot
fit.
make
You
this
can't fit it in.
mistake. I didn't know. that.
Yep.
No.
I
Okay,
got this wrong too.
36. Which of the following describes the 95% confidence interval of a 20% absentee rate in an apartment with 30 people? Okay, so how do we go about doing this? Well, we need to find the formula. So where do we find the confidence interval for our proportion formula? Well, we go look in the index for confidence interval.
How come you know the confidence interval?
Because it says confidence
You
interval.
already have this certificate, that's why.
No, because how do I know it's a confidence interval problem? Because it says confidence interval.
What page?
I don't know.
Didn't we just look at the confidence?
Yeah, we-
Well, no, we looked at a confidence interval for means. This is different. This is a confidence interval for proportions.
So that's what my question is. How do we know that if we need confidence interval for
Because it's
proportion?
giving you 20%. Percentage is a proportion.
ratio, proportion.
Okay, and what was the first one?
Means.
Because I need to understand what was the question?
How was the?
But it said a confidence interval for means.
Plus minus 3 units for a mean. Okay. Now
Yeah.
I need to see that.
Okay, so now we have proportions. So it's going to be P
Give me that.
plus minus. No, someone's gonna have to look me up because I'm
So
doing.
there's confidence interval for proportion, mean, and variations. Okay, so there are many confidence intervals.
Don't write that down yet. I'm doing this off the top of my head. You guys need to look it up in the book to make sure I'm right. I think that's the right formula.
93.
I think it's the right formula. Don't write that down yet.
I trust you.
No, please don't trust me. This is why you shouldn't do. You don't have to memorize anything for the exam. This is why it's open book.
Is P plus minus Z alpha 2 square root of P 1 minus P over N.
Yay!
That is
What is the
page.
page number?
293.
Yay! I still have a brain.
That's why it's a page number.
Okay, so write down what the problem tells us. So the problem tells us that P equals 0.2. N equals 30. They tell us the confidence level is 95%. So we should immediately write down that alpha equals 0.05. Therefore, Z alpha over 2 equals
196.
1.96, yes. Okay, so now do we know everything? Do we know P? Yes. Do we know Z alpha over 2? Yes. Do we know P? Yes. Do we know 1 minus P? Yes. Do we know N? Yes.
Okay.
So what did that happen?
We know everything. We are calculating what the interval is.
So you have to calculate for the
So you have to do the plus and the minus.
lower.
Yeah, for the you have to do the plus for the positive side of the interval and the minus for the minus side. Okay, so we can just substitute in. So 2.2 plus, we'll do the positive side first, 1.96 over 1.2 times 0.8 over 30. Now, hopefully someone's going to help me.
I don't know if I'm correct.
One can be provided for you.
It's okay.
You have a cell phone.
Okay, I'll put my calculator.
So that whole, the 1.96, that whole side is 0.143.
Okay. That looks pretty reasonable. So it'd be 0.2 plus 0.14, right?
So plus 2,
Would be 34.
0.34.
And if
or
you do
34.
you go the other way, it would be 6. 0.2 minus 0.14 would be 0.6.
Yeah.
So our answer would be
A.
I.
I don't know how
Aye,
I
aye,
do
aye,
this, but I can answer correct without applying.
You marked A?
Yeah,
How you know?
I don't know. I'm thinking 30 people, I'm just
30 people,
95%.
35%, that's what you said.
united. And 20% is the absentee rate. I use some logic, but 2 times.
Yes,
I'm using the complicated form.
Is there?
37. Which of the following are needed to calculate CP? So we already wrote down the formula for CP. CP is the upper specification limit minus the lower. I'm going to write it down instead of talking and write it down. The upper specification limit minus the lower specification limit over 6 sigma. So what do we need to know? Well, we need to know the, do we need to know the mean? Nope. Do we need to know this? We need to know the spec limits and sigma? Yeah, we need to know that. The process mean and sigma? We don't need to know the mean. Upper and lower spec limits? Yeah, we need to know those and sigma. So our answer there is B.
That's wrong.
Okay, repeatability and reproducibility.
B, he said.
B, B. Yeah, because we need to know our spec limits and sigma. Spec limits and sigma. 38.
What is sigma cap?
Sigma and sigma cap, we'll get to that when we talk about our process capability. It's about different ways of approximating the standard deviation based upon if we're looking at short-term variation or long-term variation.
I think that threw me off a little bit. Okay.
Okay, repeatability and reproducibility. Okay. Sorry about that for those of you on the video. We have to switch laptops. And unfortunately, you're not going to get the slides because we're on a different laptop. Sorry. Beth is, there's one person that attends remotely. Yeah, I know, there's lots of people. So Beth, well, all of you have the option of connecting remotely. If you miss them, you can watch these live, or you can watch them recorded. I send out the links. The links are good. There's also a YouTube playlist that has all of them stuck together. No, it has the videos. You can listen to me.
You have them 3 and 4?
No, these are the live ones.
Right.
Yeah, well, yeah. If you would, if you, as soon as you can go back and watch the first class, second class, third class. Yeah.
Go to the right. Go to the left. One is this way.
Yeah, you're fascinated by that, but we're gonna have to do something about that. Yep. Now we've done in with that. I forgot my charger this morning for my laptop because I don't have a brain. So we had to do a quick change over there. Thank you guys for indulging me. I'll be right back.
No, I just want to know that. Very aggravated.
I was saying I just started, since I've come here, I'm just like,
Punching.
because I've like my lunch, my dinner, everything.
Horrible. I'm back-to-back meetings, and then we have a big commitment to senior management this Friday. I'm out of the office tomorrow and Friday. Like I'm traveling, it's not even like a vacation, but I'm traveling. So I'm like, I have to get this stuff done.
Is that?
No, I told the she's gonna have to help them out. Because I'm traveling, I don't even have access.
Are you going anywhere good?
Georgia.
That's not good.
It's like the workload is so much that the other investigators just never like, looked at these records properly. And then they just sat with them. So then the one girl, when she left in January, she handed it over to the second guy that was named to me. So he never had time to look at it. Like, if I can sit with them and work with them, it would be done. But I have way too much other stuff going on to be able to help them manage the work. So then he sat on it. Now my guy has it, my new guy has it. And then it was such a mess the way it was managed from the beginning. Like, the final investigations were attached on Sunday. They weren't even signed off on. They weren't even final investigations. So now I have to
Once they have left it, and if you don't, do they really come and help you?
Well, the problem is that the vendors are more concerned about releasing products versus doing complaint investigations.
Do you have quality agreements with them?
Yeah. But at the end of the day, the company just
Company wants the material too, because
yeah.
that's why I'm saying quality is not a value.
No, it's not. It's
I'm really looking at now the quality to do something. Like, I would rather be regulatory, because regulatory at the end of the day gets the submission in, they get the resources. Not that I'm doing a big change, but that's a logical.
Yeah.
Cool, everyone's back, and we have a working laptop, and good time is being had by none. And you made it back in. And didn't get locked out. I apologize for not bringing the key. So
I'm
we're,
surprised that it's even open at 6.
yeah, we're not sure.
No, because we used to be across the way, and I thought there was a
Yeah,
part exit.
we thought so too. we're not, no, our facilities guy said that it was locked, and I definitely walked in after 6. So we're not sure what the deal is there, but cool. So we were up to 38 before my laptop died. So repeatability and reproducibility are terms that operationally define precision. Because bias, as we talked about, is the difference between the true value and the observed value. Accuracy is how close my measurement is to the truth. Discrimination is your ability to be able to discriminate a good piece from a bad piece. And precision is your measure for how close my measurements are to each other. How much variation is there in my measurement system? That's precision. So our answer there was D, as in dog, or Doritos, or delicious, or dinosaurs. 39. A method that classifies data without significantly reducing accuracy or precision is known as, what do we think?
I don't want to.
You don't want to think. It's too late to think. It's 8 o'clock. We're like,
I don't know why I have marked coding here. I don't know.
coding is the answer.
Maybe I read it. That's why I marked.
Yeah, so coding is an idea where you represent a number by a simplified representation of it without losing anything, but you're making it simpler for computational analysis. So the most common way you do this is to take the days of the week and make them 1, 2, 3, 4, 5. So make Monday 1, Tuesday 2, Wednesday 3.
Yes, now I remember that table. Yeah.
Or it could be, another example of coding could be, instead of having a 12-digit serial number, you just use the last 3 digits, or the last 4 digits. Those are examples of coding.
Mm-hmm.
Or it could be a transformation you do on the data, particularly when you're dealing with time, to get rid of the silly 60-minute problem. So if you're looking at the time between 1:30 and 2:17, the math becomes kind of screwy.
Mm-hmm.
So sometimes it's easier to recode the data on a different measurement system that isn't base 60. Okay, so that is 39. But we can look for each one of those terms. Bias adjustment, again, we know what bias is. That's the difference between the true value and the observed value. So bias adjustment is the idea of calibration. Statistical efficiency, we'll talk about that when we get to our hypothesis tests. Blocking is an idea in design of experiments where we de-randomize our experiment for a particular reason. Okay, and coding is a way of recharacterizing my data for computational efficiency without losing any information. So coding is the answer there. 40. Now I get to stand up in front of you and say pee-pee and watch some of you giggle.
Mm-hmm.
Redemption experiment without reason. What was it? Blocking?
Coding. What was your question? Coding is the answer to question 39.
Redemption, resemblance. That you said something about experience without the reason. That was blocking.
Oh, a blocking is de-randomization. De-randomization of your experimental design for a reason. And we'll talk about
Like blinding study and stuff.
it. Could be one of the examples of blocking is when you are dealing with an oven and the oven takes a while to reach a particular temperature. So you block all of your temperature tests you run all of them. You won't do a completely random design. You'll block them off to do that block together at that one temperature because it just takes so damn long for the oven to stabilize. Your question was bias adjustment? Bias adjustment is calibration. So it's an adjustment being made to compensate for the bias, the difference between the observed value and the true value.
Statistical efficiency is.
It's a concept we'll talk about more in depth, and I kind of can't do it justice in a one-word definition. 40. I get to say PP.
Okay, PP.
Mm-hmm.
And no one giggled. I guess you're not 5-year-old boys. 40, if a process has a variation of 4 units and a specification of 96 plus or minus 4, what is the process performance index, PP? There we go. I knew someone would giggle eventually.
I saw your face.
Oh, it's my face. She was laughing at my face. It wasn't that I said PP, it's just that I made a face. Okay, so now we have the question of what is PP? So what is PP? Well, PP, we need to figure out what the formula is. And we'll see that the formula for PP is really similar to the formula for CP.
Tolerance over sigma.
Yes.
What is the page number?
I don't know.
Oh, shit.
I don't know.
Common sufficient.
Nothing. So
Good.
again, in our procedure, what do? We first write down what the problem tells us. So what's telling us the upper spec limit is?
92. Oh, sorry, 100.
And our lower specification limit.
92.
There we go. Thanks, Dimple. And is it telling us what sigma is?
4.
No. Read the problem. Variance of 4
Variance
units.
of 4 units means square root 2.
There we go.
See?
Woohoo.
Okay, so now do we know the
Pass, we can pass.
So now do we know the upper specification limit? Yes. Do we know the lower specification limit? Yes. Do we know 6? Yeah, we know what the number 6 is, and we know what sigma is. Now it's just plug and chug. So 100 minus 92 over 6 times 2. So 8 over 12.
So,
0.4 over 6.
Correct. The difference between CP and PP is what we're going to use to approximate our standard deviation. And we'll get to that maybe tonight, probably tomorrow, next week. So 8 over 12 is equal to what?
0.6.
6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6.
We got it.
6.
7.
41. Which of the following best describes internal failure cost? So in the cost of poor quality, there are 4 buckets.
Mhm.
There is prevention,
Mhm.
appraisal,
Mhm.
internal failure cost, and external
external.
failure cost. So prevention is everything that you do to stop a screw up from happening in the first place. So it's all of your design work, it's all of your training to stop a defect from happening in the first place. Appraisal. Appraisal is the process of determining that a screw up has happened. It is all of your traditional quality functions. So it's all of your inspection costs. It's all of your machinery costs to do the inspection. Those are appraisal costs. Internal failure costs are the costs associated with a defect when it's detected at your facility. That's internal failure cost. External failure cost is the cost associated with a defect that is found when it's left your facility. So that's your warranty cost, your liability cost, your cost to send a new unit, your cost to send in a repair team, a repairman out to correct the defect once your customer has it.
How did you get sigma was 2?
Oh, the variance was 4.
Well, that's right. Okay.
Poisson.
This
No,
is
there's nothing with
also
Poisson, but it's fun to say.
565, cost of poor quality
Yes.
defines internal. External.
Everything in one.
Yeah, in one.
So a good way to reference that would be to put in your index a reference to that, so you don't have to remember it. Remember, you own the books, you can write in them however you want. So whatever allows you to search the book better, you should do it.
Are you color coded tags? Do they mean anything?
What do you got?
You mentioned
What does that mean?
server cost.
Yep.
You said, business cost.
Yep. So the cost of poor quality has four buckets. The first is prevention. The second is appraisal. The third is internal failure cost, and the fourth is external failure cost. And apparently that is on. Oh, you have a different version of the book.
This one is for the
Yeah.
tools that is finishing that around all the stuff. I think more calculation, statistical distribution.
Yep. There's 4 buckets.
Is B the answer?
Oh, there's a question.
D.
D?
Okay. Let's go through each question. Let's categorize it.
internal failure.
We'll just go through each option and let's categorize it. The economic cost associated with a catastrophic failure of an internal subsystem. Does that necessarily fit into any of the 4 buckets?
The economic cost.
Yeah, but it's the failure of an internal subsystem. Well, that could happen at your facility and can happen outside your facility, right? So we can't put that into a bucket. The unavoidable quality cost associated with the production of any product or service. No. If anything, that's going to be internal cost. The opposite of an external failure
That's
cost.
the best.
I like that. The cost resulting from non-conformance detected before a product or service is provided.
The-
That's the straight definition. So our answer there is 42.
So the
I'm sorry, the answer there is D. D. And then moving on to question 42. I was having that lovely difficulty of trying to talk, read, and scroll at the same time. There's just too many things going on. And there's only one now. 42, which is the answer to,
D.
no, but 42 is a very special number.
Because
No, Hitchhiker's Guide to the Galaxy fans?
I have no idea what you're talking about, but
The,
I know,
the,
quitting.
the book series, 42 is the answer to the life, the universe, and everything.
I don't know.
I don't think
Sorry,
Okay.
the crowd is very.
we are not on the same page.
There's a book. There's a series of books. There's even a movie. And they're really good BBC series. 42. If a histogram has a distribution that is bimodal,
Mhm.
this indicates what? So before we answer the question, we need to know what the mode is.
2 more.
The mode is the number that appears most frequently.
Mhm.
So what would cause there to be 2 modes?
Distribution is mixed.
Exactly.
Yay!
So one of the most common ways you see a bimodal distribution is in biological systems. So if I were to plot the height of all people in New Jersey, I would get a bimodal distribution. Anyone know why?
Because men and women, you can
Have different heights. They have
Yeah.
2 different distributions. There's a height distribution for men,
men,
and there's a height distribution for women.
women.
So if I were to take all the people in New Jersey, it would be about 50-50. And there would be 2 modes. There would be a mode appearing for women and a mode appearing for men.
Mhm.
So all other times you get a bimodal distribution is if you're getting parts in from one supplier or another, or off of the first production line versus the second production line. When there's some sort of underlying mixture, you'll get a bimodal distribution. So answer there is D. The distribution is mixed. 43. Which of the following best describes how an affinity diagram is used?
So 43 is B?
D.
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 Dinosaur, Doritos, delicious, dynamite.
43 is C. Grouping ideas that are created during brainstorming.
That's the whole idea of the affinity diagram. 44.
D. Prevention. Yeah, we just spoke about it.
Well,
Warranty
Well,
claims
43
are
is C.
classified.
warranty claims. So when do you get a warranty claim? When your customer has it and something went wrong.
If they're not failure, no?
No, your customer has it. If your customer has it, it's an external failure cost.
See, they tricked us.
They tricked you?
Warranty claim.
So is the D.
D. D.
D. D as in
Prevention.
no, I'm sorry. Said B as an external failure cost. Did you say B
Thank you.
originally?
We said
No, I-
B.
One of you said D.
I said D.
Okay, that's why I got confused.
That's appraisal cost, not
Yeah,
warranty.
yeah.
claims.
43. 43 was C. Grouping ideas that are created during brainstorming. That's the affinity diagram.
44.
44 is B as in boy,
Boy.
burritos, Brandon, Brontosaurus, bagels.
Okay. Yeah, I like
Bagels? See, when you leave New Jersey, you'll get rid of bagels. They don't really exist outside of the Northeast. You get bread with holes in everywhere else. Once you leave the New York area, you lose bagels.
No, actually, that's not true.
Where else are there bagels that are?
In Poland.
Oh well, they're
Because
perfect.
they're Jewish and they
Fair-
came up
fair-
with
fair-
a-
fair point, fair point, fair- fair- fair point.
Blah, 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 blah.
Fair point.
Good.
Fair point. I will further. I will further.
Yeah,
I
my
will.
first bagel I had was in Canada.
Montreal actually has really good bagels.
Well, the
So-
bagel with the hole.
We proved you wrong.
No, that's the Northeast. Where's Montreal?
That's- yeah,
Northeast.
The ones like Canada.
Yeah.
Only here.
I actually, a lot of people like New York,
That's
New
good.
York, my husband recreate because he works in Staten Island Bay, the New York side bagel, but I love
That's
Panera
the one.
bagels.
That's the one.
They're light and airy.
Yeah.
Okay.
They're
I will grant you that. I've actually had pretty good. When I was in Poland, I did have very good bagels. So yes, you're correct. Where are we up to? 45. Now that we have a little digression as to
At
what.
what stage of problem solving process would
Yeah.
be most likely cause?
So at what stage of the problem-solving process would a team most likely use a cause and effect diagram? Bum, bum, bum.
I see.
Do we collect data in a cause and effect diagram?
Actually, we do to identify the
Data.
problem,
Data is numbers.
but this is
Data
very
is numbers.
bad.
Data is numbers. Data is numbers. Data gets
Why
collected on
is
a
it data? Cause
I-
collect of data. Collection. We're going up. She suggested D was the answer.
Description of the process associated with the, see, this is not a good question for me.
Well, just think data is numbers and you'll be good.
See, organization of possible problem causes.
No, I'm not really sure,
That's
because
not
it is like,
diagram, no?
we are still telling man, more, we are talking man, machine, and
You have no
Yeah,
data.
fish
Yeah.
one. Cause and effect is fish, yes?
Yes.
yeah.
So
So what?
we are
It
looking.
It's
the
a
same.
problem analysis, root cause analysis.
So I said C.
I haven't said anything. I've just said it's not D, as in dog or Doritos are delicious. It's not D because there's no data.
But we
So you
collect
see-
reasons for root
So
cause
that's what I'm saying.
analysis.
Possible
Data is not
problem
reasons.
Causes.
Okay. A description of the process associated with the problem. We're not
No.
describing the process.
No.
No.
Define.
Definition of the problem and its scope.
See then.
No.
No.
The answer is C.
Organization.
Yes,
You
as in
remember
cat.
all possible,
cookies.
possible problems.
Organization of.
Sounds right.
Yeah.
Yes.
Yeah.
We were right from the beginning.
I didn't say you were wrong. I just didn't say anything.
Organization of possible problem causes.
Okay, 46 is a question that requires you to have knowledge of a particular machine. So the probability of you seeing a question like this on the exam is basically nil. But it's still a good question.
I think you gave an example of this. Yeah. you
I think I did
you
because
did, and
I
that's
think I
what-
did because this pops up.
And I thought of that
Just
example.
explain it to us.
Yep. Steel bars are cut on the cylindrical shafts by means of a lathe. So if you've anyone taken wood shop?
I have no idea.
Okay, a lathe is a device that takes a cylindrical device and rotates it, and you use a cutting tool as it rotates to
Like,
to change the shape of it while it's round to make like a banister for a,
oh,
or make a baseball bat.
all right. Okay.
So it's this. It rotates at high speed. You use your cutting tool and you shape
Oh,
it.
yeah, woodcraft. And?
That's what a lathe is. So the diameter of the allowable tolerance of the shafts is 2 plus or minus 1,000th of an inch. A control chart is used to monitor the quality level of the process. Seems reasonable. Which of the following plots on the control chart might indicate a problem of wear on the lathe? Okay. The diameter of a single shaft above the top, above 2,000. No, a single observation isn't going to necessarily indicate much of anything. The diameter of a single shaft below. No. An apparent increasing trend of shaft diameters. Well, as the cutting tool wears out, they're going to get thicker. So C is the answer. D, an erratic intolerance or out of tolerance diameter measurement. No, that's going to cause no, that would not be necessarily attributable to wear out. That's going to be attributable to some other problem. So the answer is C. So on the exam, you're unlikely to see a question like this because if you didn't know what a lathe was, you sort of would not be able to answer the question. So as the exam has evolved over time, it's gone from being more manufacturing specific to being more general. So if you had more of a manufacturing background, and if you ever worked in a machine shop, you would know exactly what a lathe was, or you took wood shop in high school. Or you just like to tinker with things.
Just read it. What will you get?
47, a sample consists of one or more units or products drawn from a lot or batch on the base of. What's a sample consist of? Yeah. Random selection. 48, you need to ignore the random question mark. It doesn't mean anything. I told you that when you're taking the exam. When the percent yield for a normally distributed process in which the item length specification is 5 3/4 plus or minus 4 thousandths, x is 5.72, and the standard deviation is given. What was the percent yield? Did anyone have a clue?
No.
No one had a clue. I like this question. You like the answer to the question or the question? Well, we have to draw a picture. So the first thing is it's telling us that we're normally distributed. So we should draw the normal distribution. And we know the normal distribution is defined by two things, the mean and the standard deviation. So are they telling us what the mean is? Yeah, they're telling us the mean is 57252. Right? Yeah. And they're giving us limits. Right? What's our upper spec limit?
Plus minus.
Yeah, we need the plus. 5.754, right? And then the minus is what?
48. Yes.
46. Right? So we should immediately say, are we centered? Is the mean in the center of the spec limits? So what's the distance from here to here? 002. And what's the distance from here to here? Okay, 5.752 is our mean, and 5.754 is our upper specification limit. So between 5.754 to 5.752 is 2 thousandths. Right?
Where does this 46 number come from?
The minus 5.75 minus 0.004 is 5.746. The lower limit.
Because the upper limit was
But
given.
why they are different? Why is it
Because
0.02
X
and 0.02?
is X
Uh-huh.
is 5.7.
Why is it 0.02 on one side and 1.006
Ah,
on
because
the other side?
the mean of our distribution is 5.752,
Uh-huh.
and our spec limits are based on 5.75. So our spec limits are different than our distribution. They come from two different places. The spec limit comes from the customer. So the customer says, I need to produce the part that is 5 3/4. Our process produces on average of 5.752. And we want to know what the probability is that will satisfy your customer. That's the question we're trying to answer. You cool now?
It's okay, I don't understand that. I'm not gonna bother.
Okay. Okay. So how many standard deviations do we have to go to our upper limit? So sigma is what? 0.02? 0.002? Right? So how many standard deviations do we need to go from the mean to our upper limit?
1.
1. So we have to go 1 sigma this way. And how many sigma do we have to go to our lower limit? 3. Everyone cool with that? Okay. So what do we know about our normal distribution? What percent of the data is between plus or minus 1 standard deviation?
66.
Okay, so we know between plus or minus 1 standard deviation. So we know the blue region represents 66%, right? And we know that the area of boxing between our upper and lower specification limit is bigger than 66, right? So do we know our answer already?
So you want 83?
Yeah, we know it's bigger than 66, and we didn't do any math yet.
Not when I make a wild guess.
Okay. So let's stay with this one a bit more.
Mhm.
Okay. So what do we know? Let's write down our rules. So we know plus or minus 1 sigma is 66, right? Plus minus 2 is 95. And plus minus 3 is 99.7. Okay, so how do we use this to be helpful? So if it's plus or minus 1 sigma, how much is between the mean and plus 1 sigma?
34.
Yeah, 30, half of that. So between our mean and minus 3 sigma, how much is that?
My mean
Mhm.
and minus 399.
0.7 is
Okay.
between minus 3 sigma and plus 3 sigma is
Yes,
99.7.
Yeah, half.
Half of that, right?
Yeah.
So 49.85, thereabouts, right? So to go from here to here is 49.85. And to go from here to here is what, 33, right?
Mm-hmm.
So we get thereabouts 83%. Right? Okay. Let me undo that part. Okay, so we know to go to our limit over here, we go 1 sigma, right? And to go to this guy, we go 3 sigma. Follow me that far. So between our mean and 1 sigma is 33%. And our mean to 3 sigma is 49.85, thereabouts. Plus minus 3 sigma, 99.7. So if we're going half that way, from the mean to 3 sigma, it's going to be half of 99.7, so 49 and change. So if we add those two together, we get 83 and change.
I kind of don't get why 1 sigma is 33 and other 3 sigma are 43.
Oh, okay.
If you multiply 9,
You're not multiplying by 3. You're looking at, remembering the normal distribution as the bell-shaped curve. So I told you to write down on the front of your textbook that plus or minus 3 sigmas is 66%. And since the normal distribution is symmetric, between the mean and plus 1 sigma is 33, and the mean minus 1 sigma is 33. So then on plus or minus 2 sigma is 95%. So that means from the mean to out 2 sigma is 47.5, and from the mean to minus 2 sigma is 47.5.
Okay, just a very silly analysis. You look at the answers, and then you look at what the question is. There is a mean is 5.752, and the spec is 5.75 plus minus this. So you have a mean here of 5.752. That's the mean for that given spec, and given whatever percent yield they're looking for, it seems like it's on the higher side compared to, like, you have 15, 19, 47, and it's 80, if you have to take a wild guess.
Yes, if you take a wild guess, yeah, you can
Because if that's the mean, with a standard deviation up to third decimal level and like 0.002, and that's the limit. Like if you look at the answers options, if it was very close by, like 60, 70, 80, but this definitely looks more than 50%.
Okay.
I'm just thinking,
That's fine.
Is it too bad to think like that?
I think you should draw the picture and draw it out. But if you have to resort to guessing, yeah, your intuition will help. But do you understand the logic here of how it's symmetric and how, just by drawing the picture?
Right.
When we get to this section that actually covers this material, we'll look at how to use the z-table in the back of the book to get the more formal answer. But as you see, just by the approximations that we know, we get it out to a decimal point. Just by knowing the stuff we know and those rules of thumb that we wrote down on one of the first classes. 49. In preparation for construction of a cause and effect diagram, it is important to, what's important to?
Let's see.
The answer is C. Yep. Record everything.
That's what we were doing on the first day.
Yep. Second day.
Everything.
Second day.
You said
Second.
everything.
Second day. Okay, so the answer there is C. Record everything that people suggest. Now we're up to option D, as in dog. I'm sorry. We're up to. I'm mentioning the question before I even asked it. We're up to question 50. A quality technician uses a C chart to monitor the number of defects in a square foot of material. After the initial startup period, the mean number of defects is calculated to be 13.5. What should the control limits for the C chart be? Okay, so we need to figure out what the formula is for the control limits of a C chart.
Something with 3.
Did we find that formula? C bar plus minus 3 radical C bar.
Why?
Why is it 3? Because of 3 standard deviations from the mean. Because the control limits are based upon them being 3 standard deviations away from the mean. So that basically what that says, that if we see a value outside of our 3 sigma control limits, the probability of us seeing that just due to chance alone is 3 out of 1,000. 99.7 are going to be plus or minus 3 standard deviations. So when we observe a value above or below the lower control limits, it means something weird happened. So what's C bar? C bar, get drink. C bar, get drink. No one thought that was funny?
Yeah, I thought that was funny. I could take one right now.
C bar, get drink. C bar is 13.5. So we know C bar, we know 3, we know C bar. So 13.5 plus minus 3 square root of 13.5. 24 something?
Yeah, C. I'm sorry, I calculated.
Did anyone else calculate and get C?
But I didn't get 24.42. I got like 24.48.
Anyone? Bueller? We do economics. We do economics. Do we have a concurrence?
We don't have a calculator.
Do we have a pony? Do we have a hope? Do we have a dream?
Yes, that's the last question. It's always hope. The time is on.
$24.5 is the upper.
24.5!
Yay!
It's close now.
That's fine.
And the lower
I have
is
something.
negative?
No.
2.48.
Yes.
It's C.
See.
Cool! So we made it! We survived!
Yeah, that is negative because the square root of 13.5 times 3 was 11.
Yeah, so 13.5 minus 11 is going to be 2.
Yeah.
Cool. So has everyone put out their little bubbly forms? If you haven't put out your little bubbly forms, please do so. And now, what do you guys think? Do you need a bubbly form, or you even take it? You need to take it. Okay, well, pass them into the center.
But they are biased, you know. I fixed them on the better side. I didn't fix it, but
You shouldn't have fixed them. Just put them in the middle and grab them at the end. Okay, so what do you guys think? Hard, easy, confusing? You're just tired?
there are some questions that you can actually like, you know.
Uh-oh. That's I got a 68 laugh. How close was I?
It's very close.
Oh, you got good. How many you have? You already calculated?
Yeah, you just have to take the number right, multiply by 2.
Oh, I didn't check that.
What was I, right?
Yeah.
You passed.
No, she didn't. She got a 68. She was 10 points short.
No one passed. He said it.
No, I have no idea what your scores are. You didn't hand them in yet.
I don't.
But the point is that generally you don't improve from the pretest to the midterm. It's one of those harsh realities. We've only covered about little over half the material that's going to be on the
I went down a on my the first one.
Not by much, right? 1 or 2 questions, right?
Stop.
So the real improvement happens between now and the tri-term. So when we take the tri-term, probably we're running a little bit behind, in 3 weeks from now, that's when you will really start to perform. That's when you start to do much better on the exam.
Where to find
So
out?
I
these
got the same,
exams to
but in
take?
the first online.
They're on. I will. Since you ask me this every class, I will send you the link. I will send you the link. I will send you the link. Actually, send me an email. I'm going to put it on you. Send me an email
Silly ones
asking for
about-
more questions. I'll send you the link.
I want to see that.
Okay. So, what do we think? Where are we struggling? Where's the pain point? Everywhere, right? Everywhere hurts.
I feel sad that the simple ones that I like, I think I was overthinking some of these questions.
Okay. So how do we go past overthinking? Well, we need to rely on the book, right? And because we found out that when you look in the book, it's there. You just need to know how to look in the
But
book.
this, not all of them. Like
See, for
this
example, this
one
question
error, I couldn't
49.
find it. I couldn't I was thinking.
The cause and effect diagram, it's very straightforward question, but you know what's stuck in my mind, that you have to look at the main causes, man, machine,
Mm-hmm.
environment. So instead of saying record everything that people suggest, I said focus on only what makes things go wrong in terms of those 6 criteria.
Yeah.
So
You overthought it.
That was not mine. I have different.
So how that is being almost the same
That's what you're expected.
score.
That's what's expected.
then that's what.
You're going to be flat, flat, improve.
My thing is like, I read the explanation from the book and I.
Generally, people improve like 1 or 2 questions from the pretest to the midterm. So if you improve 1 or 2 questions, you're right about where you are. If you went down 1 or 2 questions, nothing earth-shattering.
It's like she said. At the beginning, 1 and 2, I got it wrong.
Hmm?
The improved profit, that one, and like the
Yeah.
sigma that.
Just remember, on the real exam, you do not need to get 100. There's no incentive to get 100. You need 76 to 78. That's all you need.
And the one that I used the data, the collection data, I got those wrong.
Okay, so you need to know what a check sheet is. So check.
Like I'm still struggling with some of these questions because I worry I'll see them in the exam and I'll just answer them wrong.
Well, that's why you need to. That's why the best way to prepare for this exam is to keep going through the old exams and drill through them. Because as we saw when we were going over them, each question potentially could be one of the other 4.
Yeah.
Could be one of 4 problems.
Hmm.
Don't be afraid. It's only a dream.
Did you forward the exam also to us?
Yeah, I did.
Because I'll have to read it.
Yep, I had sent you the exam. There's a pile. I had sent you the exam actually earlier.
Really?
Everyone has the exam, right?
Oh. For the class.
So,
Look, today, green, this is lesson, this is
The real lesson 6. Yeah, we're
6 or 7.
this is 6. This is the same 6 that you have.
we have to say.
Yeah, we haven't got. I emailed you 7, but we're not going to get there. So we're back at 6. We're at the fake one, the one that we started going over last class. So we talked about the descriptive statistics, right? We got that far. We talked about the measures of central tendency. We talked about these, or am I?
We talked about mean, median, mode.
Okay, so we talked about what our measures of central tendency are. They're the mean, the median, and the mode. Where the mean is just the arithmetic mean. You take all the observations, you divide by the number of observations, right? Familiar with that. The median. The median is just the middle number. So if there's 5 numbers, it's the 3rd number. Then there's the mode, the number that appears most frequently. So as we saw in the exam, you can have a bimodal distribution, a trimodal distribution, which is an indication of a mixture. So the exam loves to ask you questions of the form, for the nominal measurement scale, what is the best measure of central tendency to use to analyze the data? So for nominal measurements, what measurement scale should you use? The mean, the median, or the mode?
For nominal,
So the question is testing on what nominal data is. Nominal data is putting things into categories. So yellow, green, blue. Can you take the arithmetic mean of yellow, green, blue? No.
It was a question about, you said it.
No, you can't.
At least least data. Something.
Well, the least informative measurement scale is nominal. But if I have my measurements, that's making things. The yellow ones go in that bucket. The green ones go in that bucket. The red ones go in that bucket. What's the best way to look at my data and analyze it? Well, the mode. The mode will tell you the most appropriate measure of central tendency to use for nominal data is the mode. Okay. Well, what's our next measurement scale? Ordinal. What is the proper measure of central tendency for ordinal data? The mean, the median, or the mode?
Can you repeat this question?
So what is the proper measure of central tendency for ordinal data? Remembering that ordinal data puts things into order.
puts into order, so it's like the middle one, median.
Well,
Yeah.
so it places things into order. It does that. It's also those Likert scales. So the I strongly agree, I somewhat agree, neutral, somewhat disagree, strongly disagree. What was the question back there?
What was the question?
The question is, what is the proper measure of central tendency for ordinal data? And the answer is correct. It's the median. Median. This guy.
And what did you say about the mode?
The mode is the proper measure of central tendency for nominal data. And for ratio and interval, the measure of central tendency is the mean. So that's covering our measures of central tendency. Is the mean. Well, generally the mean. The default is the mean, unless there's a reason not to use the mean. So one of the examples of a reason for not to use the mean is if your data is heavily skewed. And we'll get to that in a couple slides. So the default position is to use the mean for interval or ratio data, unless there's a reason not to. So now we're talking about our measures of dispersion. So dispersion relates to how spread out our data is. And there's four main ways that we characterize how spread out the data is. The first is the range, where you cook your breakfast. The second is the interquartile
I
range.
smiled.
Then there's the standard deviation and the variance. So what is the range? The range is the difference between the highest value and the lowest value. We know that. Or you cook your breakfast. Or your significant other cooks your breakfast for you, even better.
Now you both go and pick up breakfast.
Or someone cooks the breakfast on the range.
On the range is the key word.
Okay, so the interquartile range relates directly into the box and whisker plot. Remember the box and whisker plot? So the interquartile range is the range in the box. So it's the difference between the value for your third quartile and your first quartile. So what percent of the data is in your interquartile range? What percent of the data is between the first quartile and the third quartile? So we got one vote for 25, got one vote for 75, and I got a,
Because I have.
did I get a vote for something else? Oh, there was a vote for 50? Did I hear a vote for 50?
Because the bottom is.
Hey, before we start debating, I just want to,
Between
50
and 1.
50.
Yes.
Between Q in the box, between first quartile and third quartile.
So first is 75, the first is 25, 75 minus 25 is 50.
Okay, so you got 50.
That's what you
70
said it was.
Oh.
50. Yeah, I think I've done that mistake before, so it's 50
You-
this time.
I did ask the question before.
Yes.
And the reason I asked
The
Yeah.
first one is 25.
I missed that one. I said 75 the first time, but now.
Cool. So the answer is 50. And yes, I did ask the question before
Yeah.
because it's an important concept that I wanted to make sure you got. And I'm glad I asked it again. Okay. So the interquartile range is helpful because it allows us to know a bit about the dispersion of our data. Another way the interquartile range is used is to identify outliers. So one of the most frequent ways the interquartile range is used, that if a value is greater than plus or minus 1.5 times the interquartile range, it's identified as an outlier.
Why 1.5?
Because we have 5 fingers.
1.5?
Yeah, because I have 5 fingers. If I had 4 fingers, it would probably be 1.4, but in a base 8 system, all our numbers would be different. The reason that we have a base 10 system, right, is because we have 10 fingers, right?
No, I don't know if this is actually the equal.
No, the reason that we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we start over counting is because we have 10 fingers. If we had 6 on one hand, 6 on the other, we'd probably count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then start counting, go into the next increment. Or if we had 8 fingers, it would probably be 1, 2, 3, 4, 5, 6, 7, 8.
Okay. So 1.5 because we have 5 fingers?
Yes, it's completely arbitrary. But it's arbitrary out of 5 because, well, 5 kind of is happy because we have 5 fingers. Would you like it to be 1.6? Would that make you happier? It's good, an arbitrary selection. That's fine. You don't like arbitrary? You don't like capricious? I'll just belabor the point. So the interquartile range represents how spread out the data is between my first quartile and my third quartile. Bigger box, bigger variation. The variance. Well, we know that. We know the relation between the variance and the standard deviation, right? So, which of the two curves, the red one or the blue one, has the bigger variance?
Can you just also go, if you go back to the interquartile, how does the sigma relate to that? Sigma is also,
It's independent of that. They're two different ways of measuring the same concept of how spread out the data is.
okay.
So
you don't have to-
so sigma makes an assumption of the shape of the underlying distribution. So if my data is normally distributed, I will calculate the standard deviation one way. If my data follows another distribution, I would calculate the standard deviation a different way. So the calculation of the standard deviation requires an assumption of the underlying data, whereas the interquartile range is just line up all the data in rank order from smallest to largest and figure out where the cutoff points are.
Oh my God, it's looking like so quick. It's like,
I can professor, really can. Again. You can even watch it on YouTube and you play it on double speed. I can talk even faster like that. That would be great. Really? What? I could do that. That would make my life a lot easier. I can get to a class with
Okay.
the material even
We
faster.
understand that one. Okay. So,
So there, because there were the picture that you have here.
Yep.
Is so there is no such comparison that, or they can ask questions around with interquartile range and sigma and all that stuff together.
If they're normally distributed, they can. If they're not, if the data is not normally distributed, they can't.
But you said in our green belt,
Everything would be normally
distributed.
distributed. Yes. Yes. But but in life, not everything is normally distributed.
all right.
Okay, so my question to you going to the next slide about variance is which one has a bigger variance, the red one or the blue one?
Blue.
The blue is bigger?
Deviation.
we also know.
And you're right. Okay, so what does the variance represent? So the variance represents the average distance away from the mean. So how far is a given value from the mean? So does anyone remember what the formula is for variance?
Mhm.
I leave it off the slide so you can write it in.
Mhm.
So what-
Variance is equal to square root of x,
Yeah.
sum.
Oh, hold up in the square root.
Yeah, okay.
So we have a summation.
Mean minus sample square divided by
And
n,
minus
or depending on, yeah, if it's a sample, n minus 1. Population. capital N.
Right.
Mhm.
Okay, so you should write that in on the slide. I leave it out because if you remember, that was the first question on the exam
Mhm.
of the pretest. Cool, moving along. So distributions. So a probability distribution represents the relative frequency of occurrence of an event. And there's lots of types of probability distributions. There's the uniform, normal, exponential, bimodal, Poisson, gamma, Weibull, geometric, hypergeometric, 3-parameter gamma. Dompers. Dompers is fun. It's really fun to say. What these are mathematical descriptions of reality. So the uniform distribution is probably the easiest one, the first one you meet. This deals with things that are equally likely to occur. So the probability of rolling a 3 on a normal die is 1 out of 6. Probability of rolling a 2, 1 out of 6. Probability of rolling a 7, 0. So in a uniform distribution, the probability of each and every event is exactly the same. Coin flip. Probability of getting heads and tails is equal to the same. Okay, so then we have the exponential distribution. So the exponential distribution is a continuous distribution, and it represents the time until some event occurs. So it could be arrival times, it could be reliability, so how long until a failure occurs, and it's defined by this parameter lambda. And the mean of the exponential distribution is 1 over lambda. The variance is 1 over lambda squared. Then we have the binomial distribution. So the binomial distribution is a discrete distribution that deals with Bernoulli variables. So the probability of an event happening or not happening, heads or tails. So what's this used in? Coin flips, exam scores, stock trading, sports. Anything that has a pass, fail, good, no good occurrence. So the mean of the binomial distribution is n times p, and the variance is np times 1 minus p. The binomial distribution provides the foundation for the p and the np chart, because the p and the np chart deal with defectives. So either conforms or it doesn't conform. That's why we use the binomial distribution when using our p and np charts. So then we have the Poisson distribution. Just really fun to say.
And those were attribute charts, right?
Yes.
And that's why these are discrete.
Bingo.
Okay.
And now we have the Poisson distribution. The Poisson distribution is another discrete distribution. I once gave a talk in grad school and I could not say the word Poisson. And the paper used the term Poisson rather frequently. And I had to stand in front of the mirror and make the ploh sound for about an hour. I'm glad no one wandered by because it would just...
Poisson. Poisson.
The Poisson distribution. So the Poisson distribution is the discrete time version of the exponential distribution. So now we're dealing with count type stuff. So it could be the number of customers coming into Starbucks. It could be the number of scrapes on your car hood. It could be the number of people attending a meeting, or the number of cars going through your toll booth. So the Poisson distribution, as we saw on the exam, is defined by two things, the mean being lambda, and the variance, which also happens to be equal to lambda. So now sticking with our sorority and fraternity distributions, we have the gamma distribution. So the gamma distribution is a continuous distribution, and it's generally used for wait times. Yeah.
Because you said about the nominal distribution, the representation, P charts and NP charts.
Yep.
What about the other?
Yeah. So the Poisson distribution, it's the C and the U.
C?
Yep, and the U.
C chart and U chart, they're called count chart, and U is called,
Average count.
Oh my
and
God.
NP are called
The proportion and number.
because
Go back in that one.
Don't worry about that. We'll get to that in our other control chart section.
I
Don't.
think we have a teacher right here.
U
She knows
is-
everything.
no,
Oh, she was asking the questions.
I didn't know it.
No, because we have.
The C is the
one
count
back
chart.
In the,
Yeah,
the
because
test
sometimes
the average-
sometimes they ask a question, but
Yep, we'll get there. You guys are jumping ahead. That's next
Oh,
week.
okay.
oh, they have more coming next. Okay, cool.
Just talking about we're laying the foundation, the principles that we need
Okay,
for
this
those.
is-
So the gamma distribution is a probability distribution that is continuous, and it's used for wait times.
Continuous and?
It's continuous, and it's used for modeling wait times. So how long until something happens?
So far, we have discrete, continuous, discrete, continuous.
Yep, kind of bouncing around. And then we have the Weibull-Weibel distribution.
That's fun, bouncing around.
Why you mentioned Starbucks in the gamma if you already mentioned Starbucks in somewhere else?
Okay, because they're interrelated. Because the number of customers that walk into Starbucks, that's discrete, right? Either a customer walks in or a customer doesn't walk in. So the number of customers that walk in is modeled by the Poisson distribution.
Mm-hmm.
How long those customers wait in line, that's continuous. They can wait 2.5 seconds, they can wait 28 minutes, 20.7 minutes. That's a continuous distribution. So the arrival of the customers walking into Starbucks follows the Poisson distribution. But once they're in there, waiting in line, waiting for their beverage to pop out, that follows the gamma distribution.
Do they have any chart?
The Poisson has the C and the U. The gamma distribution does not have a control chart. And then there's the Weibull distribution, which actually on some of the Starbucks stuff, I worked with a Canadian guy, a French-Canadian guy who pronounced Weibull as Weibull. And it was kind of funny, Weebles Weibull, but they don't fall down.
Mm-hmm.
Weebles wobble. The Weibull distribution is defined by a shape and scale parameter. And what's very powerful about the Weibull distribution is by playing around with the different shape and scale parameters, you can get virtually any distribution. As you can see, highlighted up there.
It can get both.
It's going to be it's always going to be continuous. But you can get a distribution that is essentially normal, as is highlighted in green, or looks exponential, as is shown in the blue, or looks like the gamma distribution, as shown in the pink. Actually, the pink shows more of a chi-squared distribution, but you can get lots of different shapes by just playing around with the shape and scale parameter. If you go to grad school and get a degree, master's degree, or PhD in statistics or industrial engineering, you will know the Weibull distribution better than you know yourself, or at least the professors would want you to. For your purposes, know that it exists. So then we have the geometric distribution. So now we're going back to.
Just a quick question.
Yep.
The lambda is here, and what is K? Constant?
Yeah, so that's the shape and scale parameter. So the-
lambda tells you the shape,
Yes,
and
scale is K.
again, so the K, because lambda is 1 for all of these, and K is color-wise. Blue has 0.5. What does that mean?
So I'm sorry, I misspoke. K is the shape parameter, and lambda is the scale parameter. I misspoke. I apologize.
Okay, that's okay. K is the shape.
And lambda is?
The scale.
So now if you see lambda is 1 for all of them.
Mhm. But for the purposes of the exam, just know that the Weibull distribution exists. That's the background.
Okay. It exists.
It exists.
And applies on everything, virtually any distribution.
Any continuous time distribution, yep. But for the exam, no, it exists. That's the only type of question you would get. The geometric distribution is also related to the exponential. It's used for the probability of an event occurring given that something else has happened.
One after the other.
Yes.
Yeah.
Or the times until something happens, more correctly. So it's the time until you get 5 heads if you flip a coin, things like that. Again, for the purposes of the exam, no, it exists. Likewise, with the hypergeometric distribution, you should be familiar that it exists.
And these the same.
They're different. The difference is in the hypergeometric distribution, there is no replacement. So as you keep playing the game, the probabilities change. So you know there are 10 red balls in a box. As you pull out something that's not red, the probability of getting a red ball the next time goes up. That's the hypergeometric distribution.
Say that again.
In the hypergeometric distribution, you're not replacing on samples. So you have a box of parts, and you know there's 10 bad parts in that box. You know that before you start. So the probability, and there's 100 parts in that box. So there's 10 bad ones, and there's 90 good ones. So the probability on the first, when you first stick your hand in there, of drawing a bad part is 1 out of 10. So if you pick out a good part, you're not going to put it back in the bin, right? So now you've got 10 bad parts and 99 good parts. I'm sorry, 89 good parts. So now your probability has changed. So you pull out another good part. So now your probability of getting a bad part the next time is 10 out of 88. The hypergeometric distribution answers the question of what those probabilities are as you step through. Okay, so now that we've laid that foundation, we've talked about the different distributions, now I can tell you why you can forget about them. You don't need to get them, you need to know that the distributions exist. Because the central limit theorem allows us to work around our understanding of the underlying distribution. Because what the central limit theorem allows us to do is that when we sample from that distribution and we look at the averages of those samples, those averages will follow the normal distribution. So that means that regardless of what the shape of the underlying distribution is, if it's gamma, Weibull, whatever, I can make it normal. And I know how to analyze normal data. I have all these tools in the entire book, the entire toolkit to analyze normal data. So it doesn't matter what cool probability distribution I use to represent the data, it doesn't matter. I can make it normal. Because of the central limit theorem.
That's what it means, normalizing the data.
It should. It's
It is large enough. How enough and how large?
Larger than some magical number, and I'm going to give you an arbitrary.
100, it was 40 or 100. Yeah?
30. Thereabouts
When we
30.
do stability projection for stability height and all
It depends on what your data set is. It depends how distributed it is. It depends on how confident you need to be, but generally somewhere around 30. Why 30? Because, well, it sounds like a good number. Cool. Okay. So the idea here is you have the underlying distribution and you have a sampling distribution. So the sampling distribution is the averages of those samples. So I take my average on Monday, I plot it. I take my average on Tuesday, I plot it, Wednesday, Thursday, Friday, etc. And then I'm plotting those averages. That generates my sampling distribution. And what's so powerful is the average of my sampling distribution is going to be the same as my underlying distribution. Those means are going to be the same. So the mean of the sampling distribution, those average of averages, is going to be the same as the average of the underlying distribution. Everyone cool with that concept? However, the relationship between the underlying distribution standard deviation and the sampling distribution isn't the same. The sampling distribution has a standard deviation that's the underlying distribution over the sampling size, the number of samples. Okay, what do you need to know for the exam? Well, we actually have a slide answering your question. So what you need to know for the exam is the central limit theorem allows you to take non-normal data, take samples from that non-normal data, and then make it normal by taking the averages. Okay. So you have parts coming off the line. You have no idea what the shape of the distribution is for the length of the parts. What the central limit theorem says is that I can take a sample of 10 parts, take that average, plot it, take another sample of 10 parts, take that average, plot it, rinse, lather, repeat for 30 or so samples, and the plot of those averages will follow the normal distribution. That's what the central limit allows us to do. And then by analyzing that sampling distribution, those averages, I can then do my control charts, I can do my hypothesis test, all using the assumptions that are based on the normal distribution. All without having any knowledge of what the length parameters were of the underlying distribution, of how my machine is turning out the parts. I don't need to know that. Just because of the normal distribution, central limit theorem, I can normalize my data to follow the data set, the distribution that I know how to analyze the data with.
The set of the averages that you're plotting, it has to be predefined.
No, you know nothing. You know absolutely nothing. And what's powerful about that is I know the averages of my sampling distribution will be the same as the average of the underlying distribution. So just by taking these successive averages and averaging my averages, I know stuff about the underlying distribution.
So I guess that's the reason why when say we are manufacturing something and they have that study plan of take 10 samples, average weight for them.
Exactly. Well, so we want to get our data to be normal because once we get the data to be normal, we know a lot about the normal distribution. So what do we know about the normal distribution? Well, it's symmetric, right? Which means that half the data is above the mean, half the data is below the mean. We know it's defined by a couple of different things, but we also know that for the normal distribution, it's one of the few distributions where this is true, where the mean equals the median equals the mode. There's a limited number of distributions where that's true. So the normal distribution is defined by the mean and the standard deviation. We know that. It has this lovely icky formula that if you ever try to do calculus on, starts to explode. So we've seen these before, and unfortunately, I'm not as clean as I should be in terms of my nomenclature, because this really should be an S, right? And this should be a U. I am not clean. I've never seen a statistics textbook that's consistent. Sorry if you're one of those people that gets bothered by such things. You can smack my hand when I write the wrong one. I am human. Every textbook author is human. It just happens. So what is the variance? What the variance is representing is how far away on average is a given point from the mean. So let's look at what the formula is telling us. So we're taking each individual point and we're seeing how far that is away from the mean. Anyone remember why we're squaring it?
If it's negative.
You get rid of the negatives, right? Okay, so we're dividing by n because, well, that's an average, right? So then why with the standard deviation do we take the square root? So this is for the variance, right? And the standard deviation is the square root of that. So why should we take the square root of that if we're looking for the average distance away from the mean? Everyone understand the question? So we're looking for a number that represents how far on average is a given point from the mean. And the way we're doing that is we're taking each individual point and subtracting how far it is away from the mean, and we're squaring it to get rid of the negative, and then we're dividing by the number of observations just to come up with the mean. And that gives us the variance.
Now, because we squared there, so.
Exactly. So you're undoing the first squaring with taking the square root at the end. So that's the relationship between the variance and the standard deviation. We talked about what the range is. Range.
Highest.
What do you It's about 68%, plus or minus 2 standard deviations, 95%, plus or minus 3 standard deviations, 99.7%. Know it, love it, breathe it, do it, be it.
When you did that question before, you did 66%.
Yeah,
but that's
it's
you're human, right?
Yeah,
That
it's just
was
more of a rounding error.
rounding, but it was a
it's-
human error.
No, it wasn't human error. The number is like 67 and change. So it's just a matter of some people round it up, some people round it down. It's just like,
Yes. Yeah, I thought first class we said 68.4, but that's fine.
yeah, that's probably what the number is. Okay, so we talked about this. We talked about this again. So what happens when we change our mean? This is exactly the question that we had regarding the bottle filling problem in the exam. So when you change the mean, you just keep the same, you just move where the center is. Where you decrease the standard deviation, the curve becomes fatter or thinner. So which do you generally want? Fat curves or thin curves?
Thin curve.
No one made an inappropriate joke. Thank you. If you get the right population, you get a very interesting conversation there. So generally, you want less variation. Why do you want less variation? Well, because that's the whole goal of Six Sigma, is to decrease your variation. And if you're looking at it from more of a lean perspective, well, variation is a source of waste. So yes, you generally want to decrease your variation. So actually thinking ahead, or causing you to look ahead or think ahead or review to what we talked about in the midterm, what hypothesis test do we use to see if there's a statistically significant difference between the variance before treatment and after treatment? Talked about it twice.
How many?
No, between, what is the hypothesis test to use to determine if there's a statistically significant difference between standard deviations?
Standard deviation.
Or variances, yeah.
F?
Yes, the F test. Okay, so our equations for the normal distribution, we know this. So the mean, take each observation, add it up. Standard deviation, we talked about that. For the sample, we talked about that. Cool. Okay, now we're getting into the standardized Z, which will probably be our last topic for today. So the standardized Z is allowing us to translate our data to a counting unit of standard deviations. So if you remember back to the question that we did up here, where we figured out how many standard deviations away the upper control limit was and the lower control limit was, what we were doing was using the standardized Z. We were taking a given observation, so our upper specification limit, subtracting the mean, and dividing by the standard deviations. So that was telling us how many standard deviations away we were. So in the case of the upper specification limit, we were 1 Z away. In the case of the lower standard deviation, we were minus 3 Z away.
So Z is that.
It's a unit of standard deviations away a given value is.
So from the formula, X is
Your observation. The mean is the mu is your mean, and sigma is, well, sigma is your standard deviation. So what this allows you to do is answer the question of how probable it is to get a particular value. Just like we were able to say, what is going to be our percent yield based upon our distribution and these spec limits. So what's the probability I'm going to produce something that's going to be bigger than this or smaller than this or within this range? So that's where we use the standardized Z.
Can you explain how this turned like a value of 10, 15, 20, and then how the Z values are?
Oh, yeah. So the average is 25, and we see that's represented as 0 Z. Our standard deviation is 5. So if we go out to one standard deviation, would be 20 minus 25 over 5. So that would be negative 5 over 5 is negative 1. If we go to 35, so we do 35 minus 25, that would be 10 over 5, that would be 2. Which corresponds to 2 standard deviations.
So wait a minute, the X is the number that you're looking at.
Yes.
The U is the average.
Yep. And sigma is the standard deviation. So in this example, average is 25,
This was our-
standard deviation is 5. So 30 minus 25 is going to give us 5 over 5, which is 1. And of course, this holds for fractional values as well.
So for this, you need to know the standard deviation before, right?
Yes.
But if they don't give you, and this is the point, you know that this one is 1 standard deviation. 16.
Well, they would, and what generally the way you use the standardized z is you either have to calculate out your standard deviation and your mean, or they'll give you the standard deviation and the mean. So what you're generally going to use the standardized z is to answer the question of how likely is it for something to happen. So we will stop there. See you guys next week.
You will forward the video for YouTube for today?
I did that already.
For today?
Yeah.
The YouTube?
I can't
Yeah.
even turn on my phone.
But